We will learn how to specify the best RGA for your application. So if you are in the market to buy a new RGA, or you need another RGA and you don't know exactly what you should buy, hopefully by the end of this presentation you'll have a pretty good idea what will work best for you. We're going to also learn how to configure the RGA software. Once you buy it, you're going to have to work with the software for that device. We're going to learn how to configure it to track real-time changes in gas composition. And then that's going to take us to part 2. We're going to learn how to differentiate between background and process gases and how to differentiate common interactions between RGAs and sample gases. So then we're going to provide an introductory section on what is required to operate residual gas analyzers for vacuum applications ranging anywhere from ultra-high vacuum to atmospheric pressures. And that is going to be a section where we're going to essentially go through all the different sampling systems that are out there. Then we're going to learn how to quickly and effectively interpret typical RGA spectra. I'm sure a lot of you will be interested in that. And in the end, the last 15 minutes, I'm going to look at any questions you might have posted via the chat interface, and we'll try to address as many of them as possible. So we'll start with bibliography. These are the few of the books that I really like. The first one is a monograph that is published by the American Vacuum Society called Partial Pressure Analyzers and Analysis by Drinkwine and Lichtman, and I highly recommend this book. It has a lot of examples of sample spectra. I have multiple copies of this book around the place where I work, and everybody uses them constantly for reference. If you're planning on using a residual gas analyzer to sample pressures higher than high vacuum, in other words, anything different from direct immersion into a vacuum system, then I highly recommend that you check out a publication from the Journal of Vacuum Science and Technology by Blessing and collaborators. It's called Recommended Practice for Process Sampling for Partial Pressure Analysis, and it's a great paper. Pretty much no matter what you want to do in terms of gas analysis with residual gas analyzers, this paper will help you figure out how to do it. Everything I ever learned about quadrupole mass spectrometry and how to design an RGA came out of a simple book, a book by Peter Dawson, and I highly recommend it, particularly if you're interested on the instrumentation side of the technology. There is a couple articles, how to use an RGA and what else can an RGA do. These are a couple papers, articles. They're a little old now, but they're interesting because they show you ways to use residual gas analyzers in applications that are kind of, not what you would expect for a typical vacuum analysis. I also highly recommend a book, particularly if you're doing ultra-high vacuum, by John Yates, Experimental Innovations in Surface Science, where not only does he talk a lot about gas analysis, how to do surface science analysis, and so on, but also a lot of tricks for ultra-high vacuum. The most common book that I use in my lab is always Building Scientific Apparatus by John Moore. There is a new edition that just came out for that book. And in the end, we will be back talking later on about the NIST Spectral Library. This is the place where I go to get all the spectra that are needed to compare to essentially to identify the species that are in a vacuum system by comparing spectra. So we'll start a little bit talking about some of the basic concepts. We'll be talking today a lot about vacuum. Vacuum is any volume of space that is essentially empty of matter and such that its gaseous pressure is less than atmospheric pressure. Atmospheric pressure being 760 millimeters of mercury or close to it, depending on your altitude. Of course, a perfect vacuum, P equals 0, right, is a philosophical idea. It can never be achieved in real practice due to things like leaks and outgassing and so on. So an RGA, a residual gas analyzer, is very often used to measure the quality of a vacuum, which refers to how well a system is approaching this perfect vacuum, P equals 0. I'm going to use this diagram throughout the presentation. This is this is kind of like my mock-up of a vacuum system. And the idea in this, we have a vacuum chamber. This vacuum chamber is pumped by a pumping system with a pumping speed S. And even if I close that valve that is in the device, even if I close this valve, the gauge will never indicate a pressure equal to 0. We'll never get there. The reason for that will be because at a minimum, I will have leaks and or outgassing in that chamber. And that the pressure that chamber, the ultimate pressure that that chamber will achieve, will be the ratio of the gas that is coming in divided by the pumping speed of the pump. So unfortunately, because there is always outgassing in chambers and there is often leaks, the value of Q is never 0. Therefore, it doesn't matter how big S is, how big your pumping station is, you will never achieve P equals 0. So I'm going to talk about two pressure regimes in a process vacuum chamber like this one. I'm going to talk about base pressure. Base pressure is when the valve is closed. You essentially have been pumping, you pump on the vacuum system or the vacuum chamber for a long period of time, and what's left in those vacuums, you're not adding any gas to it, and what's left in that vacuum system is simply whatever is leaking in or whatever is outgassing into the chamber, and those gases are called residual gases. And this is why these partial pressure analyzers, they're often called residual gas analyzers, because the main application of residual gas analyzers is in industry is to monitor the amount of gas present in the chamber during these base pressure conditions. But RGAs also get used to measure process pressures. In that case, when you're under process pressures, what happens is you have opened the valve that is in the previous diagram. So this valve is now open, gas is being flown into the system, and some process is going into the chamber, and an RGA can still be used under those conditions. So bottom line is residual gas analyzers, even though they have this name of residual gas analyzers, which would imply that are mostly used for the analysis of the quality of a vacuum chamber under residual gas conditions, can also be used under all process conditions, including when you're delivering gas to the system. And we're going to go through how that is done. We'll be talking a lot about partial pressure today, so I want to make sure everybody knows what partial pressure means. You probably do already, but just in case. So if you have a mixture of gases inside a vacuum chamber, each gas has a partial pressure in that chamber, which is the pressure which that gas would have if it were alone in that volume. So in other words, the partial pressure of that gas is the pressure that that gas would exert on the walls of that vacuum system if all the other gases from the chamber are removed. And of course, the total pressure of that vacuum chamber, or in that gas mixture that is inside that chamber, is the sum of the partial pressures of each individual gas in the mixture. And what is the reason why we are all here today listening or learning about residual gas analysis is because we all know that the composition of a gas, that is the partial pressures or concentrations of gases that are in a vacuum chamber, is knowing what that composition is usually as important as knowing the total pressure of a vacuum system. So in other words, very often, many of us rely on a total pressure reading to know where our vacuum system is. However, as we are probably all here because we also know that in cases where we are pumping down a vacuum system, very often knowing what's in that vacuum system, what's left in that vacuum system, what the residual gases are, is just as important as knowing what the total pressure of that system is. And for that, let's just use an example, right? Imagine that you have a vacuum chamber, and you start, we'll go back to the prototypical vacuum chamber here. We close the valve and we start pumping on the chamber. And what we are after is a specific target pressure that we need to hit before we can start a process. And we close the valve, we start the pumps, and we start pumping down. And suddenly we realize that after our typical amount of time that we wait for the system to hit its target pressure, it's still not there. We have not been able to achieve that target pressure. So all we know at this point is the pressure is higher than we want. And the question we ask ourselves is, what is wrong, right? What is wrong in this system? Well, then we start asking ourselves questions. Is it a leak? Is the system leaking air from the outside and that's not allowing me to pump down? Am I outgassing water, or did I leave a screwdriver inside the vacuum system that is outgassing contaminants? Obviously, looking at the total pressure in that system is not enough, right? Total pressure alone will not be able to quickly and irrefutably tell us what the problem is. Without partial pressure information, it is always going to be a guess game. If, on the other hand, we had a residual gas analyzer in this chamber, we could go ahead and run the analyzer and collect spectra. If it were a leak, we would immediately see that we have air peaks inside, we essentially have air inside the system, nitrogen and oxygen, and we will be able to determine that it's a leak, and we would go ahead and start doing leak detection with the same residual gas analyzer by spraying helium on the outside. On the other hand, if we were to look at the residual gas analyzer spectra and we realize that all we see is water on the spectrum, so the spectra provided by the RGA is mostly dominated with water, we would know that what we have to do at that point is bake it out. So no more guessing. We know what the problem is. We know why we are not getting to the base pressure, and we also know now how to fix it. And the RGA will also let us know when the problem is fixed. So this is why I suppose all of you are here. You all realize the power of knowing not only the total pressure in a vacuum system, but also the partial pressure for the individual gases. In terms of pressure units, I'm only going to be using torr today, millimeters of mercury. I apologize for those of you that think on millibar or Pascal or whatever units you're used to, but I'm going to stick to torr. That's a unit that I use all the time, and I'm hoping that in your heads you'll be able to make the conversions as we go along. In terms of vacuum levels, when I talk about high vacuum, I'm going to be talking pressures between 10 to the minus 3 and 10 to the minus 9 torr. Ultra high vacuum, I consider ultra high vacuum anything from 10 to the minus 9 to 10 to the minus 12 torr. And obviously, as we all know today, we can even go lower than that. There are some extremely high vacuum systems with pressures below 10 to the minus 12 torr. The units for mass that we're going to use are the AMU, and I don't know how many of you are familiar with this, but this is basically how we're going to be referring to the mass of ions. And the idea with the mass units AMU is that since molecules are so small, right, it's necessary to, or it's convenient to define a special type of mass unit to express the mass of individual ions. And so what it was agreed upon is to take 1/12, right? An atomic mass unit essentially is defined as 1/12 of the mass of a single carbon atom, the 12th isotope, the 12th isotope of carbon. And this is the unit of molecular mass, which is most commonly used in mass spectrometry. So literally, when we talk about 1 AMU, we're going to be talking about a particle that has a mass of 1.66 times 10 to the minus 27 kilograms. But nobody wants to deal with exponents like these, so what we do is we normalize everything to 1 AMU, and this is what we're going to be using. What makes this unit of mass so convenient is the fact that the mass of an ion, or the mass of an atom, or of an atom, agrees with the mass number, which is the sum of the number of protons and neutrons in a molecule. So to a very close approximation, the mass of a molecule in AMUs is equal to a mass number, and this is particularly true for low-resolution mass specs such as RGAs. Okay? We're also going to be talking about ions today. An ion is a charged atom or molecule. It is charged because the number of electrons does not match the number of protons in the atom or the molecule. An atom can acquire a positive charge or a negative charge, depending on whether the number of electrons is in excess of the protons or in the efficiency relative to the protons. Most residual gas analyzers use positive ions, so we're only going to be talking about positive ion residual gas analyzers today. But be aware that you can actually buy residual gas analyzers that rely on negative ions as well, which could be a useful thing if you're trying to study electronegative molecules. Then in most of the RGAs that you buy commercially available, I would say greater than 99% again, the ions are made by electron impact ionization. So today, we are only going to be talking about residual gas analyzers that make positive ions, and we're only going to be talking about positive ions that are being made by electron impact ionization. The other important concept that we need to cover is that whereas we already talked about the mass of ions and what units are used to report the masses of ions in a mass spectrometer, it's important to keep in mind that mass spectrometers do not measure molecular mass directly, but always measure the mass-to-charge ratio of ions. So the mass-to-charge ratio is defined as the ratio of the mass number, m, of the ion, divided by its charge, q, measured in units of electron charge, e. So, for example, why is this important? Because, for example, take the argon isotope 36 and take the water molecule. The water molecule. Did everybody lose audio?
No, I'm okay, thank you.
Okay. So if you take the case of why is this concept of mass-to-charge ratio so important? It's very, very simple. Imagine you take a water molecule, right, which has a hydrogen and an oxygen. It has the combined mass number is 18, and we have an ion with a single charge. The mass-to-charge ratio for that species is 18. On the other hand, if I were to take an argon atom, this 36 isotope, that is the one that has 18 protons and 18 neutrons, and I doubly ionize it, that one would also have a mass-to-charge ratio of 18. So both of those ions, the argon 36 doubly ionized and the water singly ionized, would both show up at mass-to-charge ratio of 18. So it's very important, and they cannot be differentiated from each other by a standard RGA. So it's very important to understand that only for singly charged ions, the mass-to-charge ratio is numerically equal to the mass of the ion in atomic mass units. And so the bottom line here is that all RGA users very often refer, when they talk about a peak in the spectrum, they refer to the mass of the ion in that peak, when in reality what we are talking about is a mass-to-charge ratio. So don't forget that, because when you look at a specific peak, it could be that that's the mass of the ion if it is singly ionized, or it could be the mass-to-charge ratio of a doubly or a triply ionized atom, right? So keep that in mind as we move forward. All right. So what I want to do now is I'm going to start focusing on the hardware. So literally, what is a residual gas analyzer? What are the parts of the residual gas analyzer and how it works? So we all agreed then at this point that complete chemical characterization of a vacuum chamber, of a vacuum environment, is best done if we can do analysis of the gases present in that chamber, in addition to measuring the total pressure. Anytime that we can know what is in the chamber, right, it's very, very important information that supplements the total pressure information that pretty much all of us have in a vacuum system. The instruments that are used to measure gas composition in a chamber are called partial pressure analyzers or residual gas analyzers, and more recently, vacuum quality monitors. So today, we're going to be talking about how a partial pressure analyzer works. I'm going to focus exclusively on quadrupole-based residual gas analyzers. There is another type of residual gas analyzer called a vacuum quality monitor, which is based on ion trap technology. We do not have time today to cover that. if you are interested in that sort of technology, what I recommend is that you look for the full short course that we teach at the AVS, typically in symposia, local or international. And there I will also cover the ion trap vacuum collider monitors as well. The good news, though, is that in terms of spectral interpretation, in terms of data analysis, in terms of software configuration, both devices work exactly the same way. So what is an RGA? What is a residual gas analyzer? An RGA is a rugged mass spectrometer, small physical dimensions, that can be connected directly to a high vacuum system, and its function is to analyze the gas composition inside the vacuum chamber. So here you have a vacuum chamber with multiple ports, and there is a residual gas analyzer that is directly connected to that vacuum system, to that vacuum chamber. This sort of connection, we go back to our prototypical vacuum chamber. This typical connection where we have a vacuum chamber and we directly connect the RGA to that chamber is called direct immersion of the residual gas analyzer into the chamber. So the RGA is essentially being exposed directly to the same gases that are present inside the vacuum chamber, which, if the valve is closed, will be residual gases. If the valve is open, it could be processed gases. So in this slide, I show you an example right here where the mouse is pointing. Here is a residual gas analyzer connected to a, essentially lab-type vacuum system, directly immersed into that vacuum system. And on the bottom right corner here is a typical spectrum provided by a residual gas analyzer. And the low resolution part of the description of what an RGA is comes from the fact that the typical peaks that come out of the residual gas analyzer, they are not very well resolved. They only have about a 1 AMU resolution. And that is typical for all the products. RGAs, right, are designed for process control, for contamination monitoring in the semiconductor industry. They are used for all, for essentially any chamber in the semiconductor industry where vacuum is needed can benefit from a residual gas analyzer. So unless the environmental conditions are too nasty or too corrosive or aggressive, it's always a good idea to have an RGA there. And here are examples, right? Here's an RGA connected to a molecular beam epitaxy system. Here's another RGA connected to a cryopump station for a large ion implantation system in somebody's lab. RGAs also find applications via direct immersion in surface science, in electron microscopes, in particle accelerators. So this is a very common application of RGAs in which they are directly immersed in a vacuum system. When they are directly immersed, RGAs are often used to monitor the quality of a vacuum, easily detecting even the most minute impurities that are in that vacuum system. With an RGA, it is possible to detect gases down to constant or partial pressures as low as 10 to the minus 14 torr detection levels. This corresponds to sub-ppm detection limits in the absence of background interference. And here's an example, right, in this case, where an RGA is used to detect oil impurities in a vacuum chamber. This is the scan. This peak here is water. There is a little bit of carbon monoxide from the filament, and then some peaks here which correspond to oil as described by the library of this particular, matching the library in this particular library, which is detected by simply connecting the RGA to this vacuum chamber and looking at what the spectra looks like. The other thing I wanted to mention as well, residual gas analyzers directly immersed into a vacuum system also are excellent helium leak detectors. So those of you that are used to bringing a helium leak detector to your vacuum system might want to consider not doing that anymore if you already have a residual gas analyzer mounted to that vacuum system. Residual gas analyzers are great not only because they have a sensitivity that is comparable to a helium leak detector and sometimes exceeding it, but also because they allow you to do the measurement without having to change the vacuum system, and also allow you to do the measurements while you're actuating valves, while you're moving things around, what I call dynamic leak testing, which might allow you to detect leaks that only happen when certain actions are happening inside the vacuum system. I'm gonna be talking a little bit about this later, but this is the case in which residual gas analyzers, we are going to focus originally on the direct immersion in a vacuum system, but that doesn't mean that that's the only way to use them. Residual gas analyzers can also be used to analyze all kinds of gases. So I'm going to give you some examples of people doing volcanic gas analysis, part of gas chromatography systems where the RGA is used as the mass spectrometer of the GCMS system with field applications and so on. So anyways, we're going to start at the beginning. We're going to focus on how does an RGA work, and particularly how does the RGA work in the direct immersion mode. So as we talked before, an RGA is a low-resolution mass spectrometer. So as in any mass spectrometer, what happens is as it is immersed into the vacuum chamber, the gas molecules from that vacuum chamber or vacuum environment find their way into the RGA sensor or the RGA mass spectrometer, and a small fraction of the gas molecules are ionized into positive ions most of the time. The resultant ions are then separated essentially by mass filtering, filtered based on their mass-to-charge ratio, and they are detected and measured according to the molecular masses. That's exactly how an RGA works. It takes the gas, all of it, at the same time, ionizes the gas molecules, separates them based or filters them based on their mass-to-charge ratio. It detects the specific masses and then measures their concentration or their quantity based on their according to their molecular masses, generating what's called a spectrum in the end. Most RGAs are quadrupole mass spectrometers. That's what we're going to focus on today. And quadrupole mass spectrometers, literally what they do is they filter the ions based on their mass-to-charge ratios, as we're going to see. So we talked about this. Our main focus will be quadrupoles. So let's start talking about quadrupole mass spectrometers. Every quadrupole mass spectrometer today, and I think I'm going to prove this to you, and I'm sure if you think about whatever you have today is going to be broken this way as well, always has two parts. They're all compact, they're complete mass spectrometers, and they consist of a quadrupole probe, right, and an electronics control unit. The probe is what mounts directly on the vacuum chamber. So this is what is attached to the vacuum chamber and immersed in the gas, the same gas that is inside the vacuum chamber. The ECU, or the electronics control unit, that one connects to the probe and contains all the electronics that are required to operate the instrument. So there is a probe and there is an electronics control unit, and then a software application usually completes this package. Okay? So just to show to you, these are 4 completely different products from 4 completely different vendors, and it doesn't matter who you bought or you will buy your residual gas analyzer from, they all look the same. There's always an ECU in blue and a probe in red. This is an MKS product, ECU and probe. This is a Pfeiffer product, ECU and probe. And this is what's this called? This is the X-Tor, which is again an ECU and a probe. The boxes might look different, the probes might look a little different, but one thing I can tell you for sure, they all pretty much these days operate the same way. This is kind of like a commoditized kind of technology. So we talked about the ECU as connecting directly to the probe. So in some cases, vendors will, in some cases you might not have room for your electronics to connect to the probe the way the vendor intended it. So some vendors will offer alternative ways to mount the electronics to the probe, like in this case a 90-degree mounting configuration. In some cases too, like for example in the case of an accelerator, right, or a high-energy physics lab, or the case of a synchrotron or something like that, where you do not want to expose the electronics to the hard radiation that is in the system, you can also buy RGAs where the probe is separated from the electronics via a long cable. In this case, if you are in an accelerator or a synchrotron, it's probably going to be a radiation-hardened cable, but it will allow you to connect remotely the electronics control unit to the probe. Now, the bottom line here is, whereas you can go ahead and buy these different versions of RGAs with different configurations for the connection between the probe and the ECU, you should never, and I'm telling you this, you'll thank me later, you should never modify your ECU probe connection yourself without first talking to the vendor. The bottom line is that the connection between the ECU and the probe relies on an electrical matching between the two devices. Essentially, the ECU is electrically matched to the probe, and if you modify in any way the interface between them, it's very likely that the device will stop working. So if you have any plans of saying, I'm going to buy these, but I'm not going to be able to use it the way it is, I need to modify the ECU, you should definitely call the vendor. So here's an example of a control package, electronics control unit, the probe, the power supply, and then a little software package that goes with this. And some of the vendors are nice enough to give you the gasket to mount the RGA probe onto your vacuum system. And a typical system configuration looks like this, right? Your probe, your ECU, via some sort of interface, which these days could be RS-232, RS-485, Ethernet, USB. You connect to a PC, which is running the software. And from some of the vendors, you can also get sensor integration software such as ToolWeb or FabGuard and so on, where you can then integrate this into your semiconductor applications. In terms of the ECU itself, the electronics control units, most units look like black boxes, like this one, where there is no display. But you can also buy, if you don't want to deal with software, you can always buy a standalone box that will display the data without requiring a computer. I also like very much, there is one product out there right now that also includes in the ECU itself the ability to display some important partial pressures such as helium, water, air, so that you can use the device without any computer requirement to monitor some of the important species that might be in your vacuum system. So for example, if you're pumping down and you don't hit your target pressure and you want to know whether your system is wet or whether it's leaking, you can actually go from air to water and decide who is dominating your gas concentration, and based on that, make a decision whether you need to leak test your system or you need to do a bake out overnight. So if you don't like computers to run instrumentation because software changes all the time, or it's unreliable or it's not real time, there are options out there such as these monitoring boxes. And if you like to have an in situ display, so you don't need either a computer or an additional monitor, there are options out there as well for you. So what I'm going to do now is I'm going to break down the RGA into the probe and the ECU, and we're going to talk about the components that are in it and how they work. Okay, so we'll start with the quadrupole probe. And I'm using a lot of pictures of the SRS RGA because that's the one that I designed, therefore I have the most pictures of, but as you saw from a few slides before, it doesn't really matter what RGA you have. They're all the same. So the probe, right, this probe right here, is the place where the gas molecules are ionized, separated based on their mass-to-charge ratio, and then detected and measured as an ion current by the ECU. And here is the probe standing up with all its components. The total probe equipment consists of three parts. There is an ionizer, which is in the front. There is a quadrupole mass filter that is in the middle. And then there is an ion detector. These three parts, when you're doing direct immersion, they reside in the vacuum space where the gas analysis measurements are required. So in other words, the entire probe is inserted into the vacuum system and is immersed in the same gases that are present in the vacuum system. The ionizer, where the ions are made, the quadrupole mass filter, which separates the ions based on their mass to charge ratio, and the ion detector, which detects the ions based on their, according to their mass to charge, and then provides a signal to be measured by the ECU. Excuse me. In terms of the probe insertion, so we go back here, the probe is in some way going to go into your vacuum system. So one of the things that you got to be careful about when you buy a, when you're about to buy or when you're about to install a residual gas analyzer is what I call the probe insertion length. So check before you buy, make sure it's going to fit in your vacuum system, or whether you need additional parts to make it fit. How much space do you have? How far do you need to reach? So here's an example, right in this chamber right here. Here's an example of an RGA with a short insertion, whereas here's another example of a long, deep insertion in the device. For example, in the case of the SRS RGA that I was showing you before, you need about 2 inches, or you will need about 2 inches of insertion, right, to be able to install the residual gas analyzer in your system. You know, a typical ion gauge will take about 3 inches. So, you know, typically if you can use one of these tall gauges, you can probably use one of these in the same port. But, you know, some of the mass spectrometers, they really go in quite a bit. And you might have interference inside your system, in which case you might need to add an external tube to kind of, you know, reduce the amount of insertion. Another thing I cannot tell you enough is if you buy, just like I told you not to mess with the connection between the ECU and the probe, the other thing you have to be very aware of is before you change anything on the probe, also contact your vendor. They're not going to stop you from doing it, but they're going to help you do it right so that the device works. A perfect example is in the case of the SRS unit, is the outside nipple here should not be removed. If you remove it, it will limit the mass range of the device. Kind of a funny thing is when I was shipping this product, we used to put a little paper around it that said, do not remove these without consulting the factory. And then we would get calls saying, hey, my device doesn't work. And then I would ask, well, didn't you see like this? You know, how are you operating? Eventually I would get to the point where they would say they had removed the tube, and I would say, didn't you see the paper that said do not remove the probe? And I say, oh, no, we took it out and we threw it away right away. We never read it. So the paper was there for a good reason. If you remove this envelope from the probe, you essentially change the electrical characteristics of the device, and now the matching between the electronics and the probe is ruined, and therefore you can no longer scan up to the maximum mass that is provided by the electronics. So please read all warnings before you do any sort of modification to the probe. There's also, I was talking a lot about the possibility that you buy the RGA and it won't fit into your vacuum system because it inserts too far. Sometimes you do want to insert further into the vacuum system. So talk to your vendor. This is an example where the probe is modified. Here's a 4.5-inch con-flat flange so that the entire probe is inserted into the vacuum system, and the ionizer can be put close to where the important action in the vacuum system is taking place, where you locally need to do the gas analysis. Okay? All right. So we talked then about the probe, what it looks like, what its components are, about being careful with the amount of insertion. We also, I want to take a minute to talk about when you connect the RGA to your vacuum system, some very important recommendations. And if you look here on the left, right, this is the residual gas, this is the ECU, this is the probe right here, and this is the connection to the vacuum system. I cannot say this enough times. When you connect a residual gas analyzer to a vacuum system, at all costs use con-flat flanges and copper gaskets. If you can't, then so be it. But if you can, that is my recommendation. It's very important to realize that the ionizer where the gas analysis is going to be performed is right here, inserted in this little section of the tube. So if you have an O-ring here, or close to it, that can outgas, it can permeate gas, right? You are going to end up seeing a lot of that with the residual gas analyzer, and it might confuse you as to what is really going on in the rest of the vacuum system. So in other words, you might be contaminated by that O-ring, right? Certainly much more at the RGA than in the rest of the vacuum system, and you won't be able to tell what's going on. So here's a blow-up of that square, right? So in this case, the connection is made via a conflat port. There is a copper gasket here. You install the RGA, seal it with the copper gasket. There is no outgassing or leaks to be expected from this, and you have the best possible situation. The other thing that I'm going to recommend is, as you connect an RGA to a vacuum system, I highly recommend that when you buy the residual gas analyzer, you buy the heating jacket that comes with it. It will be optional, and you might say, I don't want to spend the money on it, but they fit the probe perfectly. They regulate the temperature very carefully, and they leave you out of this having to wrap up tape and guessing what the temperature is going to be. And believe me, over my years that I've been doing residual gas analysis and I've been selling them, I've seen everything, and I've seen multiple units come back to us that were overheated to the point where components inside had melted. So buying the heating jacket that comes with it not only bakes it out at the temperature that the manufacturer recommends anyways, but it also protects your unit, particularly for overnight bakeouts. I recommend, by the way...
Excuse me, can I ask a question?
Yes, sir.
Does it have to be copper gasket? In my application, copper is strictly prohibited. Can I put a nickel gasket or silver-plated gasket? I mean, metal gasket, but does it have to be copper?
Yeah, metal. The main concern is, as you know, right, if you put in an O-ring, right, certainly some people like to put grease with that, which will outgas.
Oh, gosh. Okay. No, I understand.
Some people like to...
Yes, I can.
Yeah, and by the way, the other thing that you have to keep in mind as well is that it's not only that you have now an elastomer gasket, close to the ionizer. Also, you got to keep in mind that the ionizer has a filament in it, an incandescent filament, and that filament will heat up the tubes that are around it. So if you have an elastomer around it, it will start outgassing more than it did. And also if it gets hot, its permeability goes up too. So you're going to start seeing all kinds of things, showing up in your spectra that are really not in the vacuum system. They're just coming out of that elastomer O-ring that you just heat it up by turning on the RGA. So yeah, it doesn't really matter what material you use. Of course, if you can't use copper, because it's going to contaminate your process, or whether it's semiconductor or whatever, then don't use it. Silver plating is fine. Whatever aluminum gaskets are fine. So, for example, if you have to use if you absolutely have to use Klein flanges, right, or quick connect flanges, then don't use rubber O-rings, but rather instead use aluminum gaskets. And you can buy, I think they're called EVAC. You can buy aluminum gaskets that operate just like the rubber gaskets, and they won't outgas and they won't contaminate your spectrum. Does that make sense?
Thank you.
You bet.
Yes, thank you.
And we talked a little about heating jackets. We have the question is, when do you bake out an RGA? The bake out is recommended. Certainly the first time you install an RGA, or once you install it, you have the RGA sitting on a shelf, or it just got shipped to you. You mount it on your vacuum system. I recommend that you do an overnight bake out. Every time you vent out to air, if you want to get to where the RGA can provide accurate results very quickly, bake out. Bake out, and if you can, bake out overnight. You should also bake out, if you're running your RGA and you're starting to get these peaks in the spectrum that you never had in your vacuum system before, and you start saying, I never had all this stuff. showing up in my spectra. They could be due to background contamination that is building up on the ionizer of the RGA. My first recommendation whenever I get a call for that is bake out the RGA. Try to boil it all off the surfaces, and let's see if it's still there. If it's still there, it's probably real. If it starts to go away, then you know it's a contamination. The other thing that is nice about this is very often if you have peaks that are kind of suspicious, you don't know what they are, and you bake out the chamber, and those peaks start to go up during the bake out, it's very likely that they're coming in from contamination. And you should always bake out your RGA over, if you start feeling that the intensity of the signals is dropping. What's happening is over time you get performance degradation, sensitivity degradation, and very often a routine bake out can restore some or most of it after an overnight procedure. So I'm not going to go through this. This is my bake out procedure, but you have access to the notes, I believe. This pretty much tells you how I recommend to do a bake out. The only thing you're going to find here you might or might not do is I always add a scrubber gas to my bake out. So if I bake out the RGA, I usually flow a little trickle of gas into the system so that I have enough gas to move the contaminants out of the system, in a little bit more, a little faster way. All right, so we talked about the two parts of an RGA, the probe and the ECU. We talked about the parts of the probe. We talked about how to connect the probe, how to bake out the probe. So now what we're going to do is we're going to go into the probe and we're going to break it down into its components. And I truly believe that the best way to take advantage of an instrument is to understand how it works. And in the case of an RGA, unfortunately, there are a lot of parts. And all of them can have problems. So the more you know about how the device works, how it's made, what its parts are, I think the better you're going to be, the more efficient you're going to be at using the device. So we're going to go into this in a fair amount of detail. So right here is a picture of an ionizer. The ionizer, as we said before, is where the ions are being formed, right? So the pressure, so here's a picture. This section right here, this is the ionizer of the RGA. This is, in this case, an SRS RGA, but it's the same in all units, doesn't matter what you buy. The pressure or the gas composition at this ionizer, right, is the same as in the rest of the analyzer, and it's the same as in the rest of the vacuum system. And the residual gas molecules, if you follow the mouse, right, they can freely go in and out of this ionizer, right, through the grid assembly. So these are all perforated metal, right, grids. And the positive ions are formed direct inside this ionizer by electron impact ionization. So in other words, the molecules, as they go through, they get hit by energetic electrons and they get ionized. What I like to talk a little about this. We're talking about how to order the best RGA. If you need to buy an RGA, what I always look for an RGA is how the ionizer is made. So most ionizers are made out of wire mesh. Sometimes you'll find made out of perforated sheet metal. They typically have cylindrical symmetry. This is what's called a brink design for ionizers. And the ionizer is kind of a cylinder that is coaxial with the axis of the quadrupole mass filter. The construction material is something that you have to pay a lot of attention to. Most residual gas analyzers are made out of stainless steel. In the case when I made mine, I used stainless steel 304, and that's perfectly fine to do with one caveat, and that is that the stainless steel 304 will outgas a lot of hydrogen. So if you're going to be doing a lot of hydrogen analysis, stainless steel 304 will not be your first choice. In that case, my recommendation would be that you talk to the vendor and ask them if they have either a moly or a platinum-clad moly ionizer. This is particularly true for UHV applications, where 95% of the gas that is left in the vacuum system is hydrogen to start with. Another option that you might find is that some vendors might say, I don't have a moly or a platinum moly one, but I have a gold-plated version of the the same ionizer, which has a much lower hydrogen outgassing level. So this is one of the things that when you're buying an RGA, depending on what your requirements are going to be for analysis, particularly if you're going to be doing a lot of hydrogen measurement in the UHV, where you really got to pay attention to what you got. And if you're going to be doing UHV, my recommendation is always ask for a platinum clad moly ionizer. What we're looking for, of course, is an ionizer that itself will have low outgassing levels. Of course, having platinum clad moly helps with that. And if you're going to buy an RGA, make sure that the ionizer is field replaceable, because it will over time get contaminated, it will need to get replaced, and you don't want to have to wait a week or two to send it back to the vendor, have them replace the ionizer, and then send it back to you. So make sure, whatever RGA you buy, that the ionizer is replaceable. So if I look at a cross-section of an ionizer, which is what this picture is, you'll find that the ionizer has 4 parts on it. And here they are. This is the outer mesh that we were seeing before, right? The little cylinder inserted into a vacuum chamber now. That is what is called the repeller. Inside there is another little cage, which is called the anode grid. Right here as a circle, and sometimes it might be like a vertical line or a halo like this, is the filament, and then at the bottom is what's called the focus plate. So there are 4 components to every ionizer, and what we're going to do is we're going to talk about each one of them. I'm sorry I'm going into so much detail, but every one of them is important. So if we break it up, right, in the next slide, you can actually see it. Here's the repeller on the outside, here's the anode grid, here's the filament, and here's the focus plate. So what's going to happen in this device? The filament is going to get really hot. Electrons are going to be formed there. They're going to be accelerated into the grid where the gas molecules are passing by. They're going to hit the gas molecules. Ions are going to be formed, and then the focus plate will push them out, will pull them out, and send them into the quadrupole mass filter. And if you look at these components in 3D, here's the repeller, here's the filament, here's the anode grid, and here is the focus plate. And this might change from unit to unit, but they're all pretty much the principal operation is always the same. So here's an example, right, of another model where the filaments are now vertical, right? But here's your repeller, here's your anode grid, here's your filaments, and at the bottom there is a focus plate. You can kind of see the hole there at the bottom. So the important thing to realize is that whereas most open source ionizers operate the same way, they are not all made equal. So depending on what it is that your specific application is going to be, you kind of want to learn about the details of your ionizer, and you can certainly do that by calling the vendor. There's always application specialists from whatever vendor you have that will be able to help you with this. So for example, in this case, right, as you can see, the ionizer is a lot smaller. So if you have space limitation issues, this might be the device for you because the ionizer is a lot smaller. On the other hand, because this ionizer is a lot smaller, it's also not as linear in response as the larger ionizer that you'll find in SRS RGA. So there's always compromises. Also, the material choices vary from manufacturer to manufacturer, and the best thing to do is, if it's not listed in the specifications, it's best to always ask, so that you're not surprised later on when you start getting funny peaks in your spectra and you don't know where they're coming from. One item that gets a lot of attention in the ionizer, of course, is the filament. I get more questions about this than just about anything else, which is, as we said before, the filament is the source of the electrons. It's where the electrons are formed that are then accelerated to the anode grid and used to ionize molecules. The way you make electrons in a filament is by heating it up to a temperature anywhere from 1,000 to 2,000 degrees Celsius. That's very, very high temperatures. It's literally incandescent. And in order to be able to do that, you have to use special materials. So you're going to find out that you can buy filaments that are made out of tungsten, filaments that are made out of rhenium, and you can also buy the new oxide coated filaments like 38 iridium or yttria iridium. So if you, I think this is the only slide I have on that, a few recommendations. If you're going to, the most general purpose filament that you can buy is, today, is an yttria coated iridium filament. They are nice because they can accept, they can tolerate inrushes of air. So if you make a mistake and you overpressurize the system, and particularly you overpressurize it with air, they will not fail because of a short overpressure condition. Whereas if you use a tungsten filament and you get an inrush of air, the oxygen will react with the tungsten, which is at about 1800 C, and your tungsten will immediately vaporize as tungsten oxide. So depending on your application is what kind of material you use. If you're going to be doing a lot of corrosive gases on the other side, for example, if you're going to be using a lot of fluorinated compounds, tungsten could be a better choice in that case because the yttria material gets, essentially the yttria goes and the yttria oxide reacts with the fluorine, and you end up poisoning the material, and you lose the work function for the emission of electrons. So the selection of the filament is something that you have to weigh very carefully. You got to look at what's your workflow. You know, am I sure I'm never going to overpressure this system? Do I have good control of my air inrush into the system and so on? Do I have good interlocks? If you don't, definitely go to yttria. Unless, of course, you have chemicals that can react with this. And if you go online, you're going to find there are several articles on these. There is a good article on the SRS website on this as well. The other thing that I'm going to recommend here, if you're ordering an RGA, is make sure that if you buy a unit that has a dual filament operation. So in other words, filaments will break sooner or later. It's a matter of time and temperature. And if you have two, then it's like having a spare in your car. So my recommendation would be don't buy an RGA that does not have a spare filament. That way, when the main filament goes, you can activate the spare filament and you can order a new filament replacement while that one lets you limp along. Usually, you get very little impact from switching to the spare filament in the device. And the other thing I recommend is when you buy an RGA, make sure that the vendor added filament protection into the software as well. So in other words, you want to have an instrument that is monitoring what the pressure conditions are, either by measuring the power delivered to the filament or using an external total pressure gauge to interlock the filament where an air inrush comes in. Okay? The second component of the ionizer is the anode grid. And the bottom line here is, as we said before, the filament is incandescent, it's emitting electrons. The electrons are accelerated into the anode grid, and that's where the ions are formed. As the electrons go through, they typically undergo a few passes through the anode grid, and eventually they hit a wire and they go away. So there is the main thing to say about the anode grid, the main thing to focus on in terms of the anode grid is to focus on, there's a setting which is the bias of the anode grid. Essentially, the anode grid is going to decide how much energy the ions will have as they go into the quadrupole mass filter. And some instruments, actually most instruments will not allow you to change what that value is, what that energy of the ions is. Some instruments will. For example, in this particular device, in this picture, you will have a low energy and a high energy setting. The low energy setting will provide you lower sensitivity, but it will also provide you narrower peaks in the spectrum, which will be better resolution, which will allow you to do more accurate identification of molecular species. The higher energy on the other side, on the anode grid, will allow you to get more, the peaks will be wider, but they'll have more signal. They'll have higher amplitude. So they're the ones that you use when you need the maximum sensitivity out of the device. So the anode grid, typically not much you need to worry about other than it gets contaminated over time. And in some of the devices, you might have to choose whether you change the energy from high to low depending on what your application is. The final item here is the focus plate. So once the ions are formed inside the anode grid, the focus plate is just a little piece of metal, right? A little plate with a hole in the middle. Its job is to attract the ions and transfer them into the quadrupole mass filter. Typically, it's kept at a negative potential, right, relative to the anode grid because it needs to attract the positive ions, right? The only way to do it is this has to have a more negative potential than this anode, and so that it can push the electron. And the main thing that you have to worry about in this device is that over time it's going to get contaminated. So you got to think about it this way, right? The ions get pushed this way. Not all of them are going to find the hole. Some of them are going to hit the plate that is between that is the focus plate itself. So once they do that, they tend to coat it over time. So because of that, you have to you got to keep an eye on that, and you got to make sure that the sensitivity of the device doesn't drop. So a very, very common reason why the sensitivity of a quadrupole mass spectrometer will drop over time is that either the anode grid or the focus plate get coated over time. For the focus plate in particular, there's usually an adjustment. It's called the focus plate voltage, and you can actually go and change the focus plate voltage over time to kind of recover your signal. But this is my recommendation to you. If you find that the sensitivity of your device has dropped over time, so in other words, the amplitude of your spectra is dropping over time, and that changing the focus plate voltage is bringing it back, it is time at that point to order a ionizer replacement kit. And my recommendation at this time is you get your new replacement kit, you replace the ionizer, as the manufacturer will tell you to do, and don't throw away the old ionizer. Keep it, because there are multiple ways to clean it. And for those of you that want to do that, you can contact me, and I'll give you a recipe on how to clean it. It requires chemistry, which I'm a chemist, so it doesn't scare me, but it allows you to essentially refurbish most of the ionizers so that the next time around, rather than go and buy another ionizer, you literally do a swap, and you can keep doing that in the future until it stops. Things get so contaminated you can't use it anymore. So I hope that helps. The final item here is the repeller cage, which is the little cage that sits on the outside of the ionizer. The repeller cage has two functions to it. The first one is to make sure that the electrons that are formed inside its volume only go to the ionizer and they don't go out. So in other words, they make sure that no electrons can escape the ionizer. That is very important for people that are doing experiments where they have electrons or where other gauges are present that use electrons for measurements. So it kind of constrains the electrons to that volume. The other thing that obviously it does, it also protects mechanically the filament from breaking it. So having the repeller in place, if you can use it, use it. If it won't fit in your device, or if you need to take it out because you want to bring a molecular beam right into the ionizer and so on, you can take it out. You're just going to have to be very careful with the filament, right? When you mount the device, that you don't crush it, or on the anode grid as well, that you don't crush it. But you can take it out. And people ask me all the time, well, isn't that going to change the sensitivity of the device? Well, no, not much. In my experience, removing the repeller in this device only affects the sensitivity by about 10%. So, you can either recalibrate the device or you can pretty much just use it. And, 10% amongst friends is probably not that big a deal. So this type of source that we've been talking about, right, which is based on electron impact ionization, and in which the gas is free to move through the ionization region freely is what's called an open ion source. So when do you use an open ion source? There are other kind of sources. This is the open variety. You will use these open ion sources to a maximum pressure of 10 to the minus 4 torr. If you happen to be buying a miniature quadrupole system, and I'm going to mention this later on, that pressure can go up to 10 to the minus 2 torr. For the traditional, standard size residual gas analyzers, the maximum pressure at which you can operate a quadrupole is 10 to the minus 4 torr. Now, keep in mind that even though you can operate the device up to 10 to the minus 4 torr, linearity between the partial pressure and the amplitude of the peaks, right, for each species, is only preserved up to about 10 to the minus 5 torr in most models. So in other words, if you're thinking you're going to make a calibration curve, right, where you say, all right, I'm going to calculate the sensitivity for this one gas, and I'm going to use that everywhere, I would not use a sensitivity factor, a linear sensitivity factor for pressures above 10 to the minus 5 torr. Most electron impact ionization sources, as I tell you, have an adjustable bias voltage and electron emission current. And that's the last thing that I wanted to touch on, which is one of the things that you can change in all ionizers is the emission current as well. And I get a lot of questions, should I operate at the default value or should I change it? This is my recommendation as far as the emission current setting for the ionizer. For most applications, the value that is provided by the vendor is the one that you want to make sure that the unit performs over its entire range of operation. In some cases, though, you might decide, I want to push the upper limit of the device to a little bit of a higher pressure. You might be able to do that by lowering the emission current. Or you might be at UHV conditions and you might say, I would like to have a little more signal. So you might actually increase the emission current in that case and get a little more signal. The thing that you have to keep in mind, though, is that every time that you change the emission current in that filament, you're also changing the temperature of that filament. And you're changing the temperature of all the tubes and electrodes and everything that is around that filament. So the amount of outgassing and the amount of background gas that you're going to get from that device will change. It's inevitable. So keep in mind, every time you change the emission current, you're not only changing the sensitivity of the device, but you're also changing the amount of outgassing that is going to occur around the ionizer as well. So you might actually see peaks come and go as you change the emission current as well. Okay? So this is kind of quick and dirty. Unfortunately, this is a condensed class, so we kind of have to go through some of these things fairly quickly, but I'm kind of giving you a taste, right, that there are all these components inside the probe, and even within each one of those components, there are parts that are important, that have parameters that need to be adjusted for different applications. And of course, we're not going to be able to address all of those today, but at least, hopefully, I'll get you thinking about, hey, maybe, I'm going to be doing UHV. Maybe I need to think about the emission current. I'm going to be operating higher pressure. I need to think about the emission current. I'm going to have gases that might coat my ionizer. I know now I have a knob to kind of get a little more sensitivity and when to order a replacement ionizer, and so on. So here's an example, right, of ionizer settings. I pulled this out of the RGA as well. Yes, sorry, it's RGA, I mean. And, this is the settings that we're talking about. There is an electron energy setting, which is how hard we hit the electrons, and I'll talk about this in a minute. We have an emission current setting, we have an ion energy setting, and we have a focus voltage. We talked about the ion energy. This is the energy of the ions in the ionizer. Typical value is 10 volts. In some devices, you get to adjust that anywhere from 2 to 12 volts. Which one you're going to use is going to depend on whether you want sensitivity or whether you want resolution. The emission current. Most devices are set to about 1 milliamp of emission current by default, but you can adjust it anywhere from 0 to 5 milliamps. If you're going to be doing UHV and you want more signal, you would go to 5 milliamps. If you're going to be going to higher pressures, you go to lower emission currents. And you know, they typically have also a minimum step that you can take. The focus voltage, like in the SRS RGA, is typically set to minus 90 volts, but you have quite a bit of adjustability. So as the unit ages, you change the focus voltage, you figure out which way you need to go, and then you make up for losses in sensitivity, and then you go ahead and you order your new ionizer. And the last item that I wanted to touch on, I always save this one for the end, is the electron energy. Actually I would say all residual gas analyzers use an electron energy of 70 electron volts. And the reason they do that is because the 70 electron volts is the energy that was used by NIST to create its spectral library. So the electron energy actually defines how hard you actually hit the molecules to remove electrons. And depending on that amount of energy is kind of what the ionization patterns are going to look for those molecules. So my recommendation to you is this. Leave the electron energy alone at 70 so that you can always use the spectral library. On the other hand, if you want more sensitivity, you can always hit a little harder with a little higher electron energy. Or if you need to start doing some differentiation where you only want to ionize organic chemicals and you don't want to ionize air components, there is also a way to lower the electron energy enough that only the organic compounds get ionized. So if that's something that you want to do, you know, if you want to buy an RGA and you want to use it so that you only see the organic compounds and you're not contaminated by all the peaks from air, you can actually set it that way. I mean, the recommendation is call your vendor. They all know how to do it. They'll give you a recommendation. It will require lower the electron energy quite a bit, and there might be tricks that they require you to do in terms of the emission current as well. But most of the time, I will leave the electron energy alone. So when you put those default settings, right, in the case of the SRS RGA, this is kind of how you do it. The 70 volts of electron energy is literally the difference in voltage between the repeller and the anode grid. The ion energy is simply the bias on the anode grid. The emission current is simply the amount of current, electron current, that is captured by the anode grid. And finally, the focus plate is simply the voltage that this plate is biased to. So that's kind of how it all comes together. What it means in this case, where I have 12 volts of ion energy and 70 volts of electron energy, means the repeller is sitting at minus 58 volts. It's negative bias, which means that it cannot touch the wall of your vacuum system. The anode grid is sitting at 12 volts, and that's how you accomplish your 70 volts of electron energy. Okay, so actually, let me see. This is pretty good. Okay, we'll talk a little bit more about electron energy. So as we talked before, the electron energy literally ends up being the voltage difference between the filament and the anode grid bias. A 70 EV is the value that is used by the NIST tables for positive direct ionization by electron impact. So it's the one that all vendors use, so you can compare spectra directly. You use low electron energies to reduce the possibility of multi-ionization and the possibility of fragmentation of the molecules, and to avoid process interferences, and I'll talk about this a little bit. You use higher energies to improve signal-to-noise ratio, so I want to get a little more signal. Boom, you hit a little harder, and you'll get a little bit more ions. And I don't know what this hurts about. Okay, so yeah, the last line is in case you want to modify your device. So here are some typical ionization curves for different gases. Now what you can see right here, right, if you look here at the bottom of the curve, is that at 70 electron volts, right, 70 electron volts, most of these gases peak in terms of their ionization efficiency. So literally this is how many ions are being formed, right? as a function of electron energy. So at 70 electron volts, most of them have peaked. The other thing that you can see too is that many of these ions do not start to ionize until you hit, say, for example, 20 electron volts, right? So it is possible, if you have a lot of organic compounds, to set your ionization energy so that only certain species, your electron energy, so that only certain species in the ionizer ionize while the other ones do not. So you can do what's called differential ionization, so where you only ionize the species that you want. So this ionization potential threshold, which is what I'm talking about, is obviously species dependent. What's going to happen too is as the energy of the electrons goes up, right, and you start hitting the ions harder, what you're going to get is the molecules now go from not only forming singly charged ions to now forming multi-charged ions and also undergoing what's called fragmentation. So here's the problem, right, is that the molecular ions that are formed by electron impact ionization are very often energetically unstable. They're left with extra energy. So not only did an electron go out, but also energy was stored in the vibrational modes. And what was going to happen is those ions will break up into smaller species. And the simplest case, right, would be the one where an ion breaks down into two fragments. One of them gets to keep the charge, and the other one is an uncharged free radical. There are all sorts of predictable fragmentation of molecules that are possible. And that means that you get, sometimes you're hitting a molecule, and instead of getting a single ion, you get these multiple ions with different masses that show up in the spectrum. These multiple ions now, of course, which are called fragmentation peaks in the spectra, complicate the spectra, but me being an analytical chemist, I look at them as they are there to help you because they facilitate the identification of species and also structural elucidation, right, if you want to know what a species is. So here's a perfect example. You take this molecule right here, right, which is hexanal, right there. I show it on the upper left corner. You hit it with electrons at 70 electron volts, and whereas you would only expect to see a peak right around here, around 100 AMU, and there is a little one, most of the spectra shows up at lower masses. And there are a lot of different peaks that correspond to different ways in which this molecule can fragment when ionization takes place. You know, then they have names. There's beta cleavage after alpha cleavage. So here's the deal. All these peaks, right, could be interfering with other species that are in the vacuum system. So they complicate your spectra, and they might complicate your ability to understand the mixture. On the other hand, they are allowing you to identify these species a lot better. If I look at a spectral library and I can match most of these peaks to a spectrum there, I most likely got that molecule right. So, in other words, fragmentation is both your enemy and your friend. And what I want to do is I'm going to show you a perfect example of how fragmentation helps you in everyday application of an RGA. And I'm going to assume that most of you have seen a spectrum. They kind of know what a spectrum is all about. But this is an example of a mass spectrum, histogram mode, collected for carbon dioxide, right? So you take carbon dioxide, CO2, right? You hit it with electrons, and you form carbon dioxide ions at 44 AMU. But you also lose an oxygen to form carbon monoxide, and these can still lose another cleave again and form carbon and oxygen ions. So all of these ions show up in the spectrum. So when you put CO2 gas in a chamber, you don't just get a single peak at 44 AMU for carbon dioxide, you also get these little fragments. And you might say, these fragments are a problem because they're going, if I were trying to see nitrogen, right, this guy would be there and it would contaminate my nitrogen signal. But as I'm going to show you, these peaks can also help you. And a perfect example is in a vacuum system where you have a peak showing up at 28 AMU. Let's take the case of carbon monoxide. Carbon monoxide has a mass of 28 AMU, right? And when you ionize it, it shows up a main peak at 28 AMU, but it also shows two peaks, one at 12 AMU and one at 16 AMU, which is the carbon peak and the oxygen peak. Nitrogen, on the other side, is nitrogen 2, two nitrogen 14s, also shows up at 28 AMU, and it fragments, but when it fragments, it breaks into a nitrogen plus and nitrogen plus has 14 AMU. So, whereas the two molecules, nitrogen and carbon monoxide, have exactly the same weight, they both fragment in a different way. So if I were to look at the spectrum, I see a peak at 28 AMU, right? And I would ask myself, well, is it carbon monoxide or is it nitrogen? How would I differentiate both of them, one from the other? Well, the first thing that I would do when I look, once I see the 28 AMU peak, I would say, okay, let's go look at what the fragments are. And if the only thing I see is a peak at 14 AMU as a fragment, I would say this is nitrogen. On the other hand, if I look and I see peaks at 12 and 16 AMU, then I would say this is carbon monoxide. Sometimes, of course, you could have a mixture of both of them. Well, then I would use the fragments to decide how much of each is contributing to the 28 AMU. So this is a perfect example where I have the same parent mass, but I have different fragments. And the fragments can help you do molecular identification and even quantification. Okay? A little more on electron emission current. So we leave fragments. I'm sure you're going to have questions about fragmentation, but I literally look at fragmentation as your friend. Of course, what's going to happen is the ratio of these peaks, right, between the parent peak and the individual peaks is going to change depending on the electron energy. So all the spectral libraries use 70 electron volt energies. So for you to be able to compare the spectrum to the carbon monoxide spectrum in the NIST library, you have to collect it at the same electron energy as NIST did. And therefore, that's why I'm telling you it's best to keep the electron energy at 70 unless you have a very specific requirement. Okay? So the next subject we want to touch on is, I'm going to take a quick look at the time. Hold on. The next item is then, I kind of want to nail the electron emission current concept so that you kind of know what to do. The electron current from the filament to the anode grid, right, is the electron emission current, and is controlled via feedback loops. In other words, when you tell the RGA to go to a specific emission current, what it's going to do is it's going to heat up the filament until that current is measured at the ionizer, and it will control the current that way, independent of what the pressure in the system is. The ion signal that you measure, of course, is directly proportional to that electron emission current. So in other words, if you look at a peak in a spectrum, and you look at the amplitude, it will follow the emission current. If I increase the emission current, the amplitude of the peak go up. If I decrease the emission current, the amplitude of the peak will go down. And so when do we change the emission current? Typically, the default will be 1 milliamp. This will be a good value to use everywhere. It's not too high to outgas too much at ultra-high vacuum levels. It's not too high to create problems at high pressure. It's good everywhere. But if I'm a UHV and I want to increase my signal-to-noise ratios for the peaks, I would increase the emission current, understanding that I might get extra peaks in the spectrum. On the other hand, I could also use lower values if I want to improve the pressure range, if I want to improve the linearity of the signal, if I want to reduce the outgassing, and also to eliminate another phenomenon that I call electrostimulated desorption. So the emission current, right, most of the time I don't touch it. If I go to UHV, very often I will increase it just to, if I'm trying to see if there are, I'm missing something on the baseline. And I will reduce it if I want to get a little more linearity, in other words, more accurate readings into higher pressures with the same device. Also, it's a good way to, sometimes what I'll do is I'll say, oh, here's a peak. I'm not sure whether this peak is coming from the RGA itself or is in the gas itself. It might be outgassing because I'm heating up the RGA. So what I'll do is I'll change the emission current between two different values to make sure that the peak doesn't follow the, the peak doesn't appear and disappear based on that emission current. And then I can say, oh, this is a temperature problem. It has nothing to do with the gas that is present in the system itself. Okay, we talked about this already. And the last thing I want to mention to you is in terms of the focus and the extraction voltage is I described to you the focus electrode as a single electrode. There are different versions of what the focus region is going to look like in ionizers. In some cases you'll have a single plate, like in this case. In some cases you'll have multiple tubes. In this case they're trying to form an ISO lens to better focus the ions into the quadrupole. But it really doesn't matter what particular design you have in this device, they all pretty much work the same way. Let me keep an eye on the time. Okay, we're doing good. One thing I also wanted to mention to you, and I'm not going to spend a lot of time on this, is the fact that recently a new technology has been introduced. It's what's called an off-axis ionizer. It's called the V-lens technology. There's a product from MKS that does this. I work at MKS, but I'm not pitching it to you because I want you to buy MKS, but rather because it's extremely useful. The idea in this case is if you're trying to do part per billion detection limits with a residual gas analyzer, you most likely need to look at V-lens technology. Now here's a perfect example, right? Here's a case of a spectrum collected without the V-lens. So in other words, the ionizer going straight into the quadrupole. And you can see there is this big line here of baseline. That baseline disappears when you put in the middle this V-lens technology. And the way this device works is it separates the neutrals from the ions. What happens is, inside an ionizer, you don't only make ions, you also make metastable radicals. If those metastable radicals go into the quadrupole axis, they can actually make ions on their own. And those ions contribute to this baseline ramp that you're seeing here. So if I get the metastables to hit this wall here, and we don't let them into the quadrupole, this baseline ramp automatically disappears because no ions are being made by the metastables in this area. And that's how you get to lower the baseline and you get to achieve part per billion detection limits. So if any of you is looking at part per billion detection limits, definitely take a look at this V-lens technology, which is commercially available now. One last thing that I wanted to talk to you about is ionizer degas. I don't know how many of you does a degas, but most of the instruments that you buy, they will have a degas option in it. And my recommendation to you is that you don't use it. So degas, degassing the ionizer, basically what it does is it increases the emission current in the ionizer typically to as much as 16 milliamps, so like factor of 10 to 15 from where it normally operates, and then increases the electron energy to values as high as 250 to 500 volts. So what happens now is they're making a lot of electrons that are flying with a lot of energy towards the anode grid, and when they hit it really hard, and they tend to remove all the contaminants that are there, right, that are on the grid. And by doing that, they clean it. And that's all great, except that you're only cleaning up the anode grid, and contamination, most likely, if it's a problem for you, is going to be everywhere. The other thing that, so in other words, you'll degas, it will look good for about 5 minutes, and then it's going to go right back to where it was. The other thing that is going to happen during degas is you're going to make a lot of energetic electrons. And those electrons are going to start ionizing molecules outside the anode grid. The ions that get formed outside the anode grid are going to bombard the filament, and as they bombard the filament, they're going to ruin it. So bottom line is you do a bunch of degases and suddenly your filament is having a hard time keeping the emission current in the device, and eventually the device fails. So whenever possible, even if you're used to degas, consider doing an overnight proper probe bakeout. And you will thank me for it. You're going to start realizing your filaments last a lot longer, and the device itself stays free of contamination for a much longer time. So bottom line here, try not to degas. And of course, if you do a degas, make sure you wait at least 10 minutes after the degas is completed for the ionizer to come back to normal temperature, because it gets really hot. In fact, the anode grid gets incandescent red. Okay? All right, so one last comment on sources here. This is we talked about an open ion source, right? And where this source is just dedicated to making ions for the RGA. There are special sources out there. There is a device, I think this is the Xtor, where they combine in the same ionizer both a standard ionizer for the RGA and a total pressure ionization region as well. Here's another example, ionizers special for molecular beam epitaxy, ionizers with ion deflectors. This is another way to deflect the ions this way and keep the neutrals going this way. There is closed ion sources. There are ionizers that have energy filters in between for plasma analysis. There are all kinds of ionizers out there. I focused on the standard Brink design cylindrical open ion source, but if you're trying to do MBE, there are special sources for you. If you're trying to do plasma analysis, and particularly you want to do energy resolved ion analysis in a plasma, there are devices that will allow you to do that. Of course, if you're going to do process analysis, we'll talk about closed ion sources in a little bit. That's another option that you will need to consider. And one word of warning, and the premise of buying a multi-purpose ionizer is that you can at the same time collect partial and total pressure. And so this is what I'm going to, and the idea is that then you don't need to buy a total pressure gauge as well. So this is what I'll tell you is this will cost you less than buying a gauge and an RGA, but you will ultimately get what you pay for. And the reason is because this design, the ion gauge, the total pressure ion gauge, of course, is not as good as a bare upper ionization gauge specifically designed for this purpose. And now a lot of the electrons only get to go once through this ionizer, so the sensitivity won't be as good. So you literally get both, but neither one of them is as good as you would get if you would get a specialized RGA or a specialized total pressure gauge. So that's my word of wisdom for this one. And I left a note here. It is possible, even though we talked only about positive ions, it is possible to get negative ion detection residual gas analyzers. They are out there. I think most of them are from Japanese vendors who are still working with these. And as you can tell, most of the molecules that are analyzed this way are very often very electronegative molecules like fluorinated compounds. Okay? One more comment that I'll do before I go into the quadrupole mass filter, because we are running out of time, is for those of you that cannot use electrons inside your source, it is also possible to do photoionization in mass spectrometers, and you can buy RGAs that also have photoionization sources as well. In that case, instead of using electrons to ionize the molecules, you use highly energetic photons, like for example from a deuterium source or a krypton source or something like that. All right, so we talked about the ionizer to death. It is now time to talk about the quadrupole mass filter. So the ions are formed in the ionizer right here, and they're transferred into the quadrupole mass filter, where they're filtered according to the mass-to-charge ratio. One by one, right, the ions pass through the quadrupole mass filter as a function of the mass-to-charge ratio, and then eventually make it to the detector. Most mass filters these days are identical in all the devices. They are all quarter-inch cylindrical rods. Construction can be stainless steel or moly rods. Typically, the spacers are made out of alumina. This is a very high precision assembly. The rods need to be parallel and in perfect quadrature to typically about 25 micro-inch tolerance, and the length of this quadrupole assembly is anywhere from 4.5 to 10 inches long, which is something you need to consider when you buy the RGA, right? Some mass specs will be very long, some of them will be shorter, so if space is a problem, you might want to check that out before you buy the device. They also, there are high-end quadrupoles that come in different rod diameters, but today we are mostly concentrated on traditional RGAs. All of those have quarter-inch rods. In terms of the material of construction, I will tell you exactly the same thing that I said before. It's okay to use stainless steel 304. The only thing that you have to keep in mind here is that you will have slightly higher hydrogen outgassing from stainless steel than you'll have from moly rods. So for ultra-high vacuum applications, I highly recommend moly rods if the vendor has, the vendor that you're considering has the option. The other thing that moly also has, it has a much better conductivity, so it's much better for the RF delivery through the quadrupole as well. So as I mentioned before, right, most quadrupoles have quarter-inch rods. There is also a whole group of quadrupoles out there commercially available, like for example this Transpector XPR from Inficon, in which case the rods are miniature rods. These are typically, I think they're about 1/32 of an inch in diameter. Same arrangement, they're in perfect quadrature. And the reason why you would go to a device like this is because they will allow you to operate all the way up to 10⁻² torr of pressure. Okay, so the principal operation of the quadrupole, they are always the same. There's always 4 rods in perfect quadrature. These are these two are positive. The opposite ones here, 180 degrees off, are negative, and the ions go in, and then both RF and DC signal applies to the rods. The rule of thumb is something like this: the mass of the in order to get the ions to go through the quadrupole, or a specific ion to go through the quadrupole, you must select a specific RF amplitude for that to happen. So during a scan, the RF amplitude is scanned from the minimum to the maximum, and one by one the ions go through. There is also a DC voltage or DC bias that is added on top of that, and that DC voltage is used then to define the resolution of the device, or the width of the peaks in the spectrum. So, in other words, in order to scan, right, and get a nice spectrum, what has to happen is the RF amplitude is scanned from a minimum value to a higher value at a constant frequency, and the DC to RF ratio is also varied at the same time to provide peaks that all have a 1 AMU resolution. And that's basically how the quadrupole works. And what you gotta keep in mind, though, is that if you look at this drawing here, right, all the ions go into the quadrupole, but only one at a time goes through. This is the one that has the red color on it. All the other ions actually go to the rods, right? They hit the rods. So one of the things that can happen here is that, particularly at the beginning, but most of them hit the rods at the very beginning, is that given that most of the ions are actually hitting here, is that contamination can start building up at the beginning, at the initial section of the rod. So if you've ever taken apart an RGA and you look into the quadrupole rod assembly, you'll find that most of the time all the contamination concentrates right here at the beginning, and that is due to the fact that the ions that don't go through, they all find the rods and they start building up a layer on that. And only one at a time goes to the detector. So, as I said before, as we generate a spectrum like the one here at the bottom, the RF amplitude is the one that selects the mass, the DC to RF ratio sets the resolution. And this is why when you do a calibration of the mass axis in an RGA, you need to put 2 gases in. You need a light gas and you need a heavy gas. So what you do is you typically use the high gas to set the RF amplitude, and you use then the low gas to set the DC value on the device. And that will calibrate both the mass axis accuracy and the resolution of the device at the same time. So I go into a lot more detail of these, when we have a full class. Today, we could spend all day talking about this. But so the bottom line is that by simultaneously varying the amplitude of the DC and the RF voltages while recording the ion currents, an entire mass spectrum can be scanned that looks like this, right? And in the x-axis is the mass, and in the y-axis is the ion current for each one of those ion signals that are coming out. So I talked to you about the fact that only one ion goes through at the same time, and then the beginning of the quadrupole gets contaminated. If that is a big problem for you, what you need to consider is the use of a pre-filter. And even there is an option of having a post-filter as well. There are some companies that sell what is called pre-filters, and these pre-filters are essentially 4 rods that are added in line with the standard rods that are only used to contain, they're only biased with the RF component. They do not have the DC. So literally what happens here is these devices, even if they get contaminated right at the beginning, and particularly contaminated by all the gases that are sticky, right, they are not affected by that contaminant because there is no DC component on the rods. And so the general rule of thumb is that a device with pre-filters, right, if there is a contamination issue, will typically last you about 3 times longer before you need to do any studies. There are a lot of papers out there. They're old, but they're still absolutely true from the early days of quadrupoles. A fellow called Brubaker did a lot of this work, and pre-filters work. They add complexity to the device, they add cost to the device. But if contamination, particularly by hydrocarbons, is a big problem for you, I highly recommend it. They do provide a little bit more sensitivity. They are less sensitive to contamination effects. And in general, they provide better resolution than standard quadrupoles, with the peaks being a little more narrow than what you see in a standard quadrupole assembly. Okay? So that's pretty much all I'm going to say about quadrupoles. Yeah, and we're doing pretty good. So the upper pressure operation of a quadrupole with the 1/4-inch rods is 10 to the minus 4 torr or less. So when you buy an RGA and they tell you the maximum operating pressure is 10 to the minus 4, that limit is really set by the quadrupole. It's a hard limit set by the mean free path of collisions between the ions and the neutrals in the quadrupole. But also remember what I told you before, that is that even though the quadrupole will operate up to that 10 to the minus 4 torr, typically the ionizers will stop being linear, they'll stop being accurate at pressures about 10 to the minus 5 torr. Okay? So, and I have mentioned here, if we are buying a miniature quadrupole, the ones like the Transpector XPR or the MKS HQ2, then that upper limit of 10 to the minus 4 torr now is extended to 10 millitorr. And that's very useful. That's 10 to the minus 2 torr. It's a factor of 100 better if you're trying to do direct immersion of an RGA into a higher pressure of gas. Okay? So, speaking of figures of merit, okay, so figures of merit for RGAs is you need to know what's the upper pressure limit of operation. You need to know what the mass range for an RGA. So if you go to buy an RGA, what they're going to tell you, or the first thing that you're going to have to decide, or that the vendor is going to ask you is, what's the maximum mass that you want to be able to measure? And what you're going to find out is that most RGAs come in models that are a 1 to 64 AMU, 1 to 100 AMU, 1 to 200 AMU, or 1 to 300 AMU. And I'm going to give you my take on this. Typically, the 1 to 64 AMU devices are designed for good hydrogen detection and nicely resolved peaks. They're slightly better resolution devices. So they'll provide you the highest quality data, qualitatively and quantitatively, and they will have the best performance at the low masses. 100 AMU is the workhorse. Most things people care about, will go up to 100 AMU. All the residual gases that are typical in a vacuum system do not exceed 100 AMU. On the other hand, my experience from having been doing for a while is that about 2/3 of all RGA people buy 200 AMU units, and the reason they do that is because of the occasional need to look at something that is above 100 AMU, like for example, you're doing xenon gas, or you're looking at a bunch of peaks at low mass and you cannot figure out what they are, and you're wondering if there is a parent ion at much higher mass, in which case you're going to need to go look up, further up in the mass range to see if the peaks that you're seeing are fragments of a much bigger molecule. And then we get to the 300 AMU unit. The people that buy 300 AMU, and there's not a lot of them, but they do it because they're truly doing gas analysis for analytical purposes. So they have all kinds of molecules, typically organic molecules, and they're trying to quantify them or look at their fragmentation patterns or whatever it is, and they need the entire range. Of course, nowadays in the semiconductor industry, chemistries are getting more and more sophisticated, with lots of precursors being these organometallic compounds and so on. So the use of higher molecular weight RGAs is becoming more and more popular. But I would say for most applications, if you ask me, right off the top of my head, what will I get? A 200 AMU is a sweet spot for ordering a unit. If you really think that all you want to do is residual gas analysis, on the other hand, stick to a 100 AMU unit, and you'll be fine. Okay? Okay, the resolution is another spec that you're going to find. It's a figure of merit for a RGA probe, and it refers to the width of the peaks. And you got to keep in mind that in an RGA, the width of the peak, which in this case is 1 AMU, is measured at 10% of peak height. So, whereas in the traditional mass spec industry, people measure at 50% height, in the RGAs, the standard is to measure at 10% of peak height. So keep that in mind. Resolving power doesn't really come up much. And then, I don't know if there's anybody on the phone here that is interested in doing low molecular weight species, like hydrogen, helium, maybe mixtures of helium-3 and helium-4, where the RGAs might have a little bit of a problem because of the zero blast problem. Well, you need to be aware that there are what's called ultra-high resolution RGAs. They're exactly the same package as what I've been showing you until now, but they are wired a little different to have a much higher resolution. They are operating in what's called the second stability region of the mass spectrometer. And these devices, if done properly, you can actually see right here in this little black screen, this is mass 1, 2, 3, 4. They can actually completely resolve the peaks here with a resolution of 1/40th of an AMU. What this means is that this mass spectrometer, configured this way, for example, can resolve helium-4 from deuterium. Okay, so if you're doing fusion, for example, and you need to be able to tell is this helium or is this deuterium, or what is the ratio of the two? Am I doing a good experiment today? The way to do it would be with one of these devices. They're also very popular for isotopic ratio measurement for helium-3, helium-4 ratios as well. And they are completely immune to the zero blast problem that affects traditional RGA. So here's a little list of different applications. One of them is earthquake early detection. This is a very interesting application a professor friend of mine is doing, where they use one of these mass spectrometers to look at the ratio of helium-3 to helium-4 isotopes that come out of volcanic areas. And it's a strict correlation that says that every time that the ratio of helium-3 to helium-4 suddenly increases above a certain level, an earthquake or a volcanic eruption will occur. And that's because the amount of helium-3 right on the magma levels is different than what you have, for example, in a oil deposit, right, which is where you typically get the helium. So if the helium-3 level starts to go up, it's because stuff is coming up from the bottom, things are moving. You might have an earthquake, or you might have a volcanic eruption. The last point to cover on the probe, and we've done pretty good here, is the ion detector. And when you go to buy an RGA, you're going to be faced with the option of what ion detector do you want. So keep in mind the ions got formed in the ionizer. They were one specific mass is filtered in the quadrupole at a time, and then that ion that makes it through goes into the detector, which is designed to collect those ions and generate an ion current. And that ion current is directly proportional to the partial pressure of that species. So what you're going to find out is that when you go to buy an RGA, there will be two kinds of detectors. There's a Faraday cap detector, and there is an electron multiplier detector. And we're going to talk a little bit about both of them. And so in this drawing right here, here's your quadrupole in this photo. Here's the quadrupole. And this section here is the detector. That's your electron multiplier. And inside right there, you can see the Faraday cap. It's in the middle. Okay? So typically, if you look at a cross-section, here's the ions are coming in here from the quadrupole. There's your Faraday cap. Here's your electron multiplier, right? The Faraday cap is typically used to measure partial pressures as low as 10 to the minus, the Faraday cap, sorry, here, measure pressures as low as 10 to the minus 10 torr. And the electron multiplier then can be used to measure pressures as low as 10 to the minus 14 torr. And you know, this is a design in the SRS RGA. These are other designs. Here's the Faraday cap, and here's the electron multiplier, right, that puts the signal. The signal comes out on this side. And here's another design, right, where the ions come in from here. They can go to a Faraday cap, or they can go into the electron multiplier. Okay? So the Faraday cap is typically a small stainless steel cup, or bucket, or plate that is located on axis. What happens is when an ion comes here, an electron comes in to neutralize it, and an electrometer measures that electron current, which is now proportional to the ion current. In this case, there is a feed-through connection to the electrometer, which then provides the measurement of the signal, and it's right here. So this cup lives right inside that little guy. On the other hand, we have also the electron multiplier. In the case of the electron multiplier, an ion comes in. The electron multiplier is biased to a negative high voltage. The ion is accelerated towards it. That's how it goes off axis. And then a chain of amplification takes place where electrons are formed. And so typically one ion comes in, and anywhere from 10 to 1 million electrons can come out on this end. So it provides amplification of the ion current. It turns the ion current into an amplified electron current. And most of the modern RGAs use what's called a multi-channel continuous diode electron multiplier. And if you're going to buy an RGA today, I highly recommend that you get one that has this, because they have the longest lifetime. Okay? So I was talking to you about the two ways. Here's what happens depending on whether you have, you're going to use the Faraday cap or the electron multiplier, and you can have both in a unit. As an ion comes in, if the electron multiplier is not turned on, it will go into the Faraday cap, right? An electron will come in to neutralize it and will measure an ion current at the electrometer. On the other hand, if the electron multiplier is turned on, it will be biased to a negative voltage. As the ion comes in, it will find its way into the electron multiplier. It will not reach the Faraday cap, and now the electron current will go, amplified electron signal will come out here, and it will measure by the electrometer through this connection now. So two independent connections, one for the Faraday cap, one for the multiplier. And typically, the electron current you get here is equal to the ion current multiplied by a gain, right? And that gain is set by adjusting the high voltage on the multiplier. I hope that makes sense. So what are the advantages and disadvantages of these devices? Well, the Faraday cap, right, detector measures the incident current, ion current directly. So the ion comes in, an electron is sent out to neutralize it, and the current is measured. The advantages, of course, are simple, stable. So really, it has no problems with dynamic range. As the ions come in, they will be neutralized. It has no mass dependence and no pressure dependence. The only caveat, though, is that the detection limit is only 10 to the minus 10 torr. Right? Now, On the other hand, if you get a, okay, so actually, let's leave it at that right now. The Faraday cap, by the way, too, is the one that sets the sensitivity of the device. So when you say an RGA has a sensitivity of 10 to the minus 4 amps per torr for nitrogen ions, that current is for nitrogen ions measured with the Faraday cap only. So the Faraday cap is the one that sets the sensitivity of the device. For most RGAs, you're going to have to make a decision at the beginning whether you want an electromultiplier or not. Here's the good news. The vendor is going to try to sell you an electromultiplier because it's a costly add-on, and you make more money out of it. On the other hand, if you're not absolutely sure that you need it, for example, if you're never going to go to the lowest pressures, below 10 to the minus 10 torr, you don't really need it. In that case, what you can do is you can say, okay, I'm going to buy with a Faraday cap, and later on you can send it in for an electromultiplier upgrade, and they will retrofit it for you. So, when do I recommend an electromultiplier upgrade? If the RGA is routinely operated below 10 to the minus 8 torr. When you want to operate at the same pressures that you've been operating on, but you want to scan faster. The electromultiplier gives you more signal and allows you to scan a lot faster, needing a lot less averaging. It will also be required when you need more dynamic range. So in other words, if you need to look, you got to pull the noise down, right, and get a little more dynamic range in your noise floor. So it will be very typical, right? You'll run an RGA with a Faraday cap. You see so many peaks, you turn on the electromultiplier, the bottom of the scan drops out, new peaks show up, and you have now enhanced dynamic range. And of course, you will need an electromultiplier if ion counting is required, and I will not get into ion counting at all. So with an electromultiplier, typical detection limit, 10 to the minus 14 torr. The gain, which is adjusted by adjusting the high voltage on the multiplier, can be anywhere from 100 to, in fact, you can adjust it to 10 if you want, but typically between 100 and 10,000. Increasing the gain any further than this is not a good idea because the signal increases, but so does the noise, so you don't get any improvement in signal-to-noise ratio. So when it comes time to buy an RGA, you got to decide between electromultiplier or no electromultiplier. Here are the advantages and disadvantages. Of course, in the advantages is high gain, which gives you faster scans, better signal-to-noise ratio. Electron discrimination, which means any electrons coming from the source you will be blind to. They give you the option of doing ion counting. And of course, they are field replaceable, which means that you can replace them anytime you want because they are consumable. But they have some disadvantages, that is, their gain degrades over time, so you're going to have to calibrate their gain routinely. And most software packages will give you the option of doing that. They have the mass discrimination, so in other words, the gain is mass dependent. So hydrogen, nitrogen, for example, hydrogen being lighter than nitrogen, will have different gains, which you are going to need to calibrate against if you want to do quantitative measurement. Also, they saturate, so their linearity of your signal will degrade sooner than they do with the Faraday cap, and you're going to need to check that out. That depends on vendor to vendor, but the 10 to the minus 5 limit will probably drop even further to perhaps 10 to the minus 6, or in some cases 10 to the minus 7. And then one thing that you have to be, let's see, yeah, okay, I'm going to say it right now. One thing that you're going to have to be very careful about is if you do have an electromultiplier in your system, you can bake out the probe as high as 300 degrees C. So typical electromultipliers will take a 300 degrees C bake out, but you cannot operate them at a temperature higher than 100 C. So do not apply high voltage on a multiplier at a temperature greater than 100 degrees Celsius. Okay? So the next slide, if you have the slide, simply I show you here how the gain, right, in the electromultiplier depends on the high voltage. And you can tell, right, it's a pretty steep curve. It's kind of a log curve on this side, right? It's a linear log curve. And you can get a lot of gain out of these devices, and typically you'll go above a gain of 1 million if you're doing any sort of ion counting. Most software packages will allow you to adjust the gain automatically, and the way they do it is very simple. They will measure the ion current with a Faraday cup. Then you will say what gain you want. They will multiply that Faraday cup current by the gain, and then they will switch to the electron multiplier and start increasing the electron multiplier voltage until the signal coming out of the multiplier is equal to the Faraday cup signal times the gain that you requested. At that point, the high voltage is set, and you have a calibrated electron multiplier for the specific gas that you use to do the calibration. Okay? One thing that you're going to keep in mind too is that electron multipliers have a limited lifetime. Typically, they start degrading after about a coulomb of charge was ejected from the multiplier. So when you buy an RGA, and particularly when you buy the software, look for RGAs and software packages that include what's called peak skipping functions. So in other words, they will skip the big ions. If you're just trying to see little ions, right, little peaks in the presence of large peaks, you can configure it so that the large peaks are not exposed to the multiplier during a scan. They're skipped, and that will significantly increase the lifetime of your electron multiplier. Okay? So this leaves us to the very, very end here. I believe we are getting, so you bought your RGA, you made all the right choices, the right mass, you have your right specifications, you got your heaters and all that, and you start using it. What are all the things that you're going to have to do to mass specs moving forward? Well, unfortunately, there's a lot of work to be done with RGAs, and we're not going to have time here to go through all of these, but I want you to kind of be aware of all these. You will need to replace filaments on RGAs. You will need to replace ionizers. The filaments, degrade and eventually break. Ionizers get contaminated and eventually need to be replaced. The quadrupole eventually will get contaminated, and it will start showing lower sensitivity. You'll have to do what's called a probe cleaning. You will have to, if you have an electron multiplier, you will have to replace electron multipliers every now and then, and there are ways to even refurbish the old one. In terms of tuning, you will have to do every now and then a mass tuning. This is very rare. I would say probably out of all the RGAs I have, maybe over the 20-something year I've been doing this, I've only seen a couple RGAs go out of tune, but it's something that you might have to do, especially if you're messing around with the settings. You will need to adjust the sensitivity on these devices, particularly if you're switching to different gases, and you will need to tune it if you're going to be doing big rate and you need quantitative measurements. So these are the things that you're going to have to do routinely to the device as part of its maintenance and tuning procedures. And I'm going to give you a couple comments here. In terms of filament replacement, ionizer replacement, you got to make sure when you buy an RGA, like you can see right here, right, that the ionizer is field replaceable. There's no reason in this modern age and time, right, that you have to send the unit back for refurbishment. It's costly, it causes a lot of delays for you, and there is just no reason why you couldn't make a design where the user can replace it on their own. In terms of probe cleaning, some manufacturers will allow you to take apart the device and clean the rods yourself. If you're inclined to do that sort of thing, if the manufacturer tells you that it's possible, and I would encourage you to do it. You'll learn a lot during it. You'll save yourself a lot of time and a lot of downtime, and it will kind of teach you a little bit how the device works. In terms of the electron multiplier and the filament, I also recommend that if you buy a unit, just order a replacement with it. So have a filament always available, have an electron multiplier always available, because all it takes is one bad mistake and you might need to replace one or both. In terms of mass tuning, the sensitivity tuning and lick rate tuning, most modern software packages will help you and will guide you through that procedure. Okay? So here's an example of a simple replacement of a filament. Here's an example of a unit where the only way you can replace this multiplier is sending it back to the vendor. Here's the lady at the factory taking it apart. In this case, all you need to do is remove this screw, the multiplier goes out, you put another one that is identical to it, and you're off to the races. That's what, here it is, right? You take that screw out, remove the multiplier, and you're put a new one in, put the screw back in, and you're off to the races. If you're inclined to do things yourself and you're okay doing it, that's the way I would go when buying one of these guys. There's a slide here that tells you how to clean an electromultiplier. I recommend you look at it. So in other words, your multiplier goes bad and you have to replace it. Don't throw away the old one. Put it through this cleaning procedure. It might save you next time. Okay? I'm not going to talk much about the electronics control unit. Typically mounts directly on the probe unless you have a separate wire. Most of them operate with a 24-volt DC connection, though some of them, like this one, has a little backpack that allows you to connect directly to the wall. And the main thing that I'm going to tell you is when you buy an RGA, right, when you look at the back, you typically have the power connector, right, where you power the device. You have the interface port, and this is, your RS-232, your relays, and whatever. What I highly recommend is get an RGA if you can, where you actually have LEDs that indicate the status of the device. So this one will tell you if the unit is on, if the filament is on, if the electromultiplier is on, and so on. And I'll tell you, we have different versions of RGAs in our factory, and there are some of them where the RGA is sitting up straight and you can't see it. So what we'll do is we'll put dental mirrors so we can actually see the LEDs. This information here is critical. The operator at the factory, right, is constantly looking at the LEDs to say, is my filament still on? Can I vent the system now? Is it safe? Do I need to go turn the filament off? Did I have an error? Is my power on? And so on. So I'm a big fan of status LEDs if you can have them. And of course, this is another great trick, right? I really love this, and I wish more vendors would do this, where you actually get your helium, your water, your air levels right here, so you don't even have to have a computer connected to it. Hold on. Yeah, this is some warnings here in the use of the RGA. I'll let you read this later. There's a funny one here. It says, do not lean on the ECU or step on it. So typically the electronics control unit is well attached to the probe, but it's not attached well enough that you can step on it. And I cannot tell you how many units I got back where people use them as a step stool in their vacuum system. There are a lot of electronics in the ECU, anywhere from power supplies to control biases to an electrometer, RF and DC power supplies. Perhaps the most critical component is the electrometer in it, which has a very tall order of measuring pressures, anywhere from 10 to the minus 15 to 10 to the minus 7 amps. And this table in this page here, it shows you essentially what the scan speed is, what the single mass measurement time is, and what the baseline noise is for the electrometer at each scan speed setting, which is essentially a dwell time setting, the amount of averaging. This table should be provided by every vendor, and if it's not in the manual, you should request it, because this is the table that you're going to use later on to decide at what scan speed or what kind of dwell time you're going to have to set the unit so you have the detection limits that you're looking for. So for example, in this unit, all SRS RGAs get sent out with default scan speed 3. In that case, it takes 400 milliseconds to collect a single ion signal, and scan millisecond per AMU. It takes, if you're doing 100 AMU, let's see, single mass scan millisecond, yeah. So it's 400 milliseconds per AMU to perform a scan, and then the minimum pressure, detectable pressure, is 1.5 E minus 14 amps, which if you divide that by the 1 E minus 4 amp per torr sensitivity of the device, will tell you what the detection limit for the device is in torr. Okay? So this is a table that I use all the time to decide how I'm going to set the mass spec in terms of amount of averaging that I'm going to use. And I'll tell you, most vendors will not provide this to you in the manual, but they can provide it to you if you ask for it. Okay? Okay, so the last thing I'm going to measure, the last thing I'm going to mention here out loud, you'll have the slides for the other one, which are pretty clear, is the concept of sensitivity. When you look at a brochure for an RGA, you're going to find a number which is called the sensitivity factor. And typically, the sensitivity factor for an RGA using the ferrite cup is 10 to the minus 4 amps per torr. What does that mean? What this means is that if you were to, and if you could, which you can't, right? But if you were to put a torr of nitrogen at 28 AMU, right, of mass into that RGA, and you were to measure the amount of current at the 28 AMU peak that comes out, you would get 10 to the minus 4 amps. Okay? So that is the number that you need to be able to turn the currents, the peak currents that you measure with the RGA into pressures. And here's the thing that you have to keep in mind. The sensitivity of the RGA is different for different gases, but the RGA uses the same sensitivity factor for all gases. So when you look at the y-axis, you know, the partial pressures that are displayed on a spectrum, they are all calculated, all those peak amplitudes in partial pressure are calculated assuming that all gases have the same sensitivity factor as nitrogen. So they are nitrogen equivalent readings, okay? So that's very important to keep in mind because the RGA is, as the mass increases, become less sensitive. The sensitivity goes down. So using this sensitivity of 10 to the minus 4 amps per torr for all the species means that RGAs will overestimate the concentration of gases below 28 AMU, and they will underestimate the concentration of gases above 28 AMU. That's just the way it goes. It's part of the territory. So as you keep an eye on the partial pressures, always repeat to yourself in your head, you know, okay, my partial pressure of krypton is 10 to the minus 8 nitrogen equivalent, okay? So that's what I say here. A single sensitivity factor is used to calculate all partial pressures in analog scans. The sensitivity factor is based on nitrogen. All partial pressure readings must be labeled as nitrogen equivalent readings. Okay? So one last comment I'm going to make on sensitivity, on calibration and tuning is a lot of people ask me, how do I make sure that every day my RGA is operating properly? Okay? How do I make sure that the sensitivity is right? How do I make sure that the mass axis is set right? How do I make sure that I'm today where I was yesterday and that I believe what I'm seeing? And this is my recommendation. My recommendation is that you get yourself a calibrated a mixed gas calibration cylinder with a calibrated leak in it. And I give you here a couple places that sell them, Vacuum Technology and Lacotech. What these little cylinders right here do is you can connect them to your vacuum system, and if you open them up, they will allow a mixture of gases to go into your system. And in this slide I show you the one that I typically use, which has helium, argon, and krypton in it. So every single day when you are ready to run, if you want to know if your RGA is doing as well as it was doing the day before, what you do is you open up your cylinder valve, you let it into the vacuum system, and you look at the spectrum. And you compare it to the spectrum that you got yesterday. If it looks the same, if the amplitudes are the same, if the peaks are the same width, you're ready to go. If something is different, something doesn't look right, something is going to have to be fixed. And if I can give you a piece of advice, is to buy one of these devices, particularly if you do a lot of quantitative measurements, and put it in your vacuum system. And on the left here is an example. In this product, the cylinder is already built into it. So the software will automatically ask you, do you want me to go and check if today we are the same as yesterday? And if you're not, it will tell you that it's not. Okay? One last piece of advice is all RGAs provide a total pressure measurement. All of them do, and I call this a marketing total pressure measurement. Do not use it if total pressure is really important to you. There is no substitute to buying a dedicated total pressure gauge. And I do not say that because I work in a factory where we make total pressure gauges. I'm saying this to you because there is no way that an RGA, the way that total pressure measurement is done, will ever match the accuracy of an ionization gauge, or even a Pirani gauge for that matter. So don't rely on the total pressure measurement of the RGA for your total pressure measurements, general pressure measurements in your system. In terms of interface, as we said, right, the ECU then has to connect to a computer. There are all kinds of interfaces today, RS-232, RS-485, DeviceNet, Ethernet. There are converters for all of these things. I don't have much to say other than about this, in terms of recommendation, other than, I would always use the fastest interface that you can find. And if you are going to do your own, you're going to not use the software that comes with the product, or rather you're going to use the software that is, you're going to build your own software, you're going to talk to the instrument directly. Make sure that the product has an available command set that allows you to communicate with the product. You might say, well, all products should do that. Not all of them do. In some cases, the company will require that you sign a non-disclosure agreement in order to be able to get a copy of the command set from them. So my philosophy is if they weren't smart enough to come up with a command set that is in the public domain, they're probably not smart enough to make an RGA. You probably shouldn't buy that one, but that's just my personal opinion, and we all have one. In terms of software packages, when you buy an RGA, I'm also going to make a distinction. There are two kinds of software packages you can buy. There are the softwares where you literally turn it on and it will start providing an analog scan right away. There's also software packages that are more process specific, and what they will require you to do is create a recipe. So you literally write a script and you're going to tell the RGA what you want it to do. Which one you choose is going to depend completely on your application, on your workflow. What I would strongly recommend is, if the software is going to be very important to you, ask for a demo version of the software. Most of the software packages will run in demo mode. So get it, make sure it works, have the applications people from the company come and help you and do it. And if you're going to be doing LabVIEW, your own LabVIEW development, most of the companies that make RGAs do have LabVIEW development kits available. Okay. Web-enabled instrumentation is also available. In this case, you literally connect the computer via an Ethernet connection, open up your browser, and via Java they will communicate with the RGA directly. They are a great way to go. They also let you do remote access. They are great. We don't use them in the factory because it's limited what they can do in terms of communication. But if this is really a device you use every now and then to just do, casual leak detection, this is one way to not have to have specific software in your computer connected, and you can just use basically any laptop out there. Okay? So this brings us to the end of what I call the hardware section, which is pretty good because this leaves us, if I'm not doing the math right, we have, it's 1:30, we're going until 3 my time, so we have an hour and a half left. This leaves us with my last slide that I'd like to look at, because this is where there is proof whether you learn something or not, right? And so when you go to buy an RGA, this is kind of the spec sheet that you have to look at. And one of the things it's going to show you is what mass ranges there are. We talked about mass range, right? That's the maximum mass that you can scan with the RGA. And as expected, in this case, you have a 100, 200, and 300 MU. And we talked about when to buy one or the other. What kind of mass filter? Well, it's a quadrupole system. These days you have to say, because there's the ion trap. What kind of detectors you have? You have the Faraday cap and you have the electron multiplier. We talked about both of them, right? This is the standard one. This is if you want gain. Resolution. This guy is telling you right here, my peaks are 0.5 AMU at 10% peak height per the AVS standard 2.3. As you can tell, the AVS has had a lot to do with defining all the standards for qualifications of residual gas analyzers, and that's one of the missions of the American Vacuum Society. So this is basically telling you how wide the peaks are going to be, which gives you a sense of the resolution of the device. And then there is the sensitivity, which we talked about this. It says 2 times 10 to the minus 4 for the Faraday cup, right? And this is, it says, it's, you can adjust, and it tells you under which conditions of the ionizer this is done. What this means is that, again, what we talked about before, 2 times 10 to the minus 4 amps per torr means that if I have a torr of nitrogen, I'm going to get 10 to the minus 4 amps of current. Of course, you're not going to have a torr because you can operate there, but it says that if you're at 10 to the minus 5 torr of nitrogen in your vacuum system, your peak is going to be 2 times 10 to the minus 9 amps in amplitude, so 2 nanoamps. Minimum detectable partial pressure, we talked about this. With the Faraday cup, in this case, is 5 minus 11 torr. When you turn on the electron multiplier, you get more dynamic range. Now you can measure down to 5 times 10 minus 14 torr. The operating pressure, in this case, they'll tell you, hey, you can operate all the way from UHV to 10 to the minus 4. The 10 to the minus 4 is set by the quadruple. But be careful, if you put an electron multiplier, I don't want you to go any higher than 10 to the minus 6, right? And part of it is multipliers nowadays can take higher pressures than that, but linearity is seriously compromised. So the vendor is telling you, don't use it above that, you know, you really don't know what you're getting. And then there's a bunch of other things like, what's the maximum operating temperature, right? This is 70 C. Well, this is telling you, don't heat anything up above 70 C. Bakeout temperature 300 C. Of course, you got to disconnect the electronics. And this is set, the maximum is set by the electron multiplier. What kind of ionizer design you have, and what kind of ionization mode. And then the materials. These are the materials that are exposed to your vacuum system. And you know, one gentleman asked me, well, what do I do if I can't use copper in my system? Well, you know, you look at this list right here, and there is copper, right? So the question for this gentleman would be, well, can I use this in my vacuum system given that it has copper? Does the vendor have an alternative material? Should I would call them, right, and make sure that this thing is compatible with your application. Filament options, in this case you have a Thoria filament. And it goes on, ranges of electron energy. But my hope is that with what we talked about, even though I had to go through it fairly quickly, so a lot faster than I do during a face-to-face short course, that you'll be able to look at these and make intelligent choices or educated choices as to what it is that you want to get. Okay? I'm not going to go into the miniatures. The last comment here is cost. How much do you pay for an RGA? You can buy RGA systems from $3,500 to $25,000 these days. It's all over the place. The reality is most of these systems are all the same. It doesn't matter what you buy. They all pretty much have the same specs. And you know, if you go look at the specification, you'll see that yourself. But what you have to be very careful about is very often low cost goes with no help. So in other words, you're not paying much for the unit, but you're also getting no help for the unit. So what I have found in my experience all this year doing this is vendors that charge more money is because they're willing to have an applications engineer either talk to you or can visit you or install it for you or train you on their use. And of course, somebody's got to pay for it. So depending on your level of comfort on learning new technology, depending on your level of comfort on installing a new piece of equipment in your system, my take would be is if you are a self-starter and you're comfortable with instrumentation, I will always go for the cheapest one. If you need more help, I would pay a little more. You probably won't get more performance in terms of what the device itself does, but you're going to get a lot of help. And, you know, that might be priceless, right? The other thing too that I always say, if you go down towards the bottom there, always price compare and go around and shop around. You know, if you call a vendor and you say, you know, I'm about to buy your competitor's unit for this much, can you match the price? Very often they'll do it. They won't leave money on the table. They won't let you go. So use that, and if you are in a university, ask for the educational discount. These devices are good to put in the hands of students so that when they graduate, they use them in their job. And so companies understand that they need to educate students, you know, on their use so that they can carry this technology into their work in the future. So as far as mass range, we already covered that. Keep in mind that there is no real volatile compounds above 350 AMU. So this is the reason why it makes no sense to have an RGA that has a mass range higher than 300 AMU unless you're buying an illegal instrument where the samples are getting heated in spot. Okay? So this is the end of my first section, which was very equipment heavy, very much dedicated to making sure you know how an RGA works and how to specify. Okay? So let's see how I how do I do this? I'm going to go to the second one now.
Are we going to get a break?
We could.
We definitely need
one. So, Keith, what do you think?
Yeah, for the next 2 minutes if you need, or anything like that.
2 minutes.
Okay.
I'm an old man.
Yeah, me too. Trust me.
Takes a little longer than 2 minutes.
All right. You want to do 145 or whatever? Whatever 38 you are. Should we go to 45?
10 is fine. 10 minutes is great.
Okay.
I'm sorry. I'm just messing with you guys.
Yes, that would be nice. Thank you.
Okay, thank you. You want to do, it's 1:50 here my time, so 3:50 your time, right? What do you want to do? Again, so we're going to have, we have about an hour almost. So what as I look at my slides, what we're looking at is part 2 now, and I believe everybody has access to these downloads, right? To the download of these presentations. So this is what I'm going to suggest in the interest of time, and I never intended to cover all of these slides. A lot of them are just for you to keep, to be able to go to. But this second section is focused on sampling gases at higher pressures, how to use the software, and how to use RGA software, and also how to do residual gas analysis. I took a look at the questions that were posted on the chat, and it looks like probably the best thing to do is to start with residual gas analysis. So the assumption here is we are going to go after the people that are using the RGA connected directly to a vacuum system. They are high vacuum or ultra high vacuum, and they are using the RGA to figure out, is their vacuum system clean? Is their vacuum this is a high quality vacuum with only the species that I allow there? Are things going well? Am I going to hit my base pressure? Am I close to the ultimate pressure of the system, and so on? So I'm going to leave for the end because I didn't see any questions on these. The other options, which are to do higher pressure sampling, including atmospheric sampling. So the good news is that there are pretty good slides on that here that you can go and touch on. But I figure, based on the question that I have, it's probably best if we focus on understanding background signals and understanding how to do spectral interpretation. Okay? So we'll jump straight to, let's see what slide. It's called residual gas analysis. There you go, residual gas analysis. And so the term, as we mentioned before, right, the term residual gas analysis, or residual gas, refers to those gases that remain in a vacuum system when the majority of the atmosphere previously occupying the vessel has been pumped out, right? So even though those residual gases may be in tiny little concentrations, right, in very small amounts, their presence could still be very significant to your process, right, or to your research experiment that you're trying to do, where you require a specific target level of residual gases in the system. So what the main application of residual gas analyzers is for people that are routinely trying to bring their system back to a residual gas environment that is consistent day after day, so that they get a consistent process or a consistent experiment. Okay? So the important thing to realize is that when you pump on a system, you know, that little valve is closed, I'm not adding anything else, you pump on it, the ultimate pressure that you're going to get in that system will be limited by two sources: gas leaks, you know, gas leaks through O-rings, valves, mass flow controllers, any kind of joints, and outgassing. Those are the two things that we're going to have to think about. So you have your RGA mounted in a chamber, you think you pumped out all the gas, maybe you baked it out, there's still stuff left in there. That stuff that is left there is either coming from leaks or is coming from outgassing. As we said before, the total pressure only tells you whether you got there or you didn't get there. But even if you got the total pressure, you still don't know if you got the right stuff in the chamber. And that is what the RGA is going to tell you. So the first thing, and there was somebody that left a question, he was saying, I think it was he, I don't know if it was he or she, I don't remember anymore. He was saying, I have an RGA in a ultra-high vacuum system. We routinely pump down to 5e-11 torr. We bake out the RGA. I turn on the RGA, and I still see outgassing from it. You know, it's just not going away. We're going to be talking about that. So this is why you're still seeing stuff in your system. The idea is the RGAs just run hot, and they have a lot of internal surface area. So the RGAs themselves contribute gas to the residual gas environment through outgassing. That's what I will call from now on the RGA background. So in other words, you know, in your case where you have a system at 5-11 torr, which is awesome, right? It takes a lot of work to get there. It takes a lot of attention to details, right? What you're telling me is you do everything you know how to do. You bake out the RGA. You've done all the cleaning that is humanly possible. You turn on the filament and you still see the pressure in the system go up. And the reason that is happening is because you're turning on a hot filament, and when you turn on the hot filament, you're heating up that filament and also all the surrounding areas through radiative processes. And so stuff that wasn't outgassing before now is outgassing. Stuff that wasn't permeating before perhaps is now permeating, right? Maybe leaks that weren't there might start manifesting themselves, though that's more unlikely. So the thing that is going to be critical for you is to understand that, no, you will never get the RGA to not give you a contribution of gas, of background gas to your gas environment. What is going to be critical is you learn to differentiate what is already in your chamber and what is being contributed by the RGA through its background outgassing, okay? And the other thing, too, that is important to realize is that outgassing that occurs from the RGA itself, right, will depend also on the usage history of the RGA, the filament material that you use, the materials that are used to construct the probe, and even what the ionizer settings are, okay? So, in agreement with the question that you asked earlier on about, you know, I did everything I could, but I'm still outgassing. Baking out the RGA is indeed the best and most common way to minimize the influence of RGA background gases, but at a pressure like yours, 5-11 torr, I don't care how much you bake it out, you will always see something coming out of the RGA when you turn it on. I have a good friend of mine. She works in the extreme high vacuum in the 10-13 torr, and very often tells me, I use your RGA, but when I turn it on, I'm dominated by the background gases. It's all I see. And then I have to go and you know, find as minor components whatever was already in my vacuum system. That's just the nature of the business. What this brings me to is a very important concept, which is a lot of people like to, you know, in installations or in factories, they will buy one RGA and then they'll roll it around from vacuum system to vacuum system to do diagnostics. My general recommendation is like that old potato chip commercial, get your own, right? And if somebody comes to borrow yours, you hide it, right? You throw a blanket on and you hide it, because you really don't want to share it. Because where the RGA has been will have a lot to do with what you see coming into your vacuum chamber as background gases when you turn it on, okay? So, what are common background gases in an RGA? And this is, if you know these, if there is anything that you need to know about RGA analysis, is this list, okay? So, the most common RGA background gases that you're going to find in just about every scan, and I'm going to show you some examples of that, are hydrogen, water, fluorine, carbon monoxide, carbon dioxide, methane, and a soup of hydrocarbons, okay? So, so remember that list: hydrogen, water, sometimes fluorine is a peak at 9. So hydrogen is at 2 AMU, water is at 18 and 17 AMU, fluorine at 19 AMU, and I didn't write them here because I'm giving you spectra for each one of them. Carbon monoxide at 28, carbon dioxide at 44, methane at 16, and hydrocarbons starting at 43. So here's a typical spectrum, and you might say, hey, this looks kind of funny on the screen. What's going on? It's in log scale, okay? So which is another thing that I'm going to recommend. You always plot the partial pressures in log scale in the y-axis. What you actually see is starting from the left side, there is a peak at 1 AMU and one at 2 AMU. This is hydrogen. It will be in just about every vacuum system. You will see hydrogen always because hydrogen dissolves into stainless steel during the manufacturing process, and it will outgas from your vacuum system forever. Your grandchildren will see it. There is no way you're ever going to get rid of this hydrogen from the system. Then as we move up, there is a little 16 peak. That's most likely a fragment from a hydrocarbon. Then there is the 17 and 18 peaks. The 18 is highlighted in red because that was what I used for calibration. That's your water in the spectrum. This one actually has a 20 and a 19. This is from hydrofluoric acid that was present in this system. So this system has water and hydrofluoric acid. Okay. The next spectrum right here, right, is a spectrum for water. And you can actually see, right, there is a peak at 18 AMU, there is a peak at 17 AMU. The peak at 18 AMU is H2O+. The other one, 17, is HO+, so a fragment where water has lost the hydrogen. You will always see water in your spectrum, and very often it will dominate the spectrum unless you are like the person that was doing the 5-11, in which case most of the water has been baked out. Now here's the deal. Every time you turn on the RGA and you turn on the filament will get hot. It will start outgassing water all by itself, but it will also start radiating infrared radiation onto all the adjacent surfaces, which will get hot. If you touch the area around the ionizer, it will feel warm. Well, outgassing is directly related to temperature. So as soon as the filament turns on and the surfaces start heating up, stuff that wasn't outgassing at a consistent rate, had a low Q value for outgassing at room temperature, now is outgassing at a faster rate. So you will actually see an increase in pressure in your chamber due to the release of water. So in the case of the UHV system, unless you did a pretty good job also outgassing the RGA, what you might find is that you turn on the RGA the first time, water comes up, and then pretty soon then it goes away. And all that has happened was that you didn't properly outgas the RGA, the water started outgassing from the ionizer, it went up, and then eventually started to go away again. The other two species, right, going back to our list, right, hydrogen coming out of the stainless steel, it will come out at a higher rate, of course, once you turn on the filament because you're heating up the surfaces and the permeation out of the stainless steel increases. Water coming out of the surfaces, it's absorbed. I have a note here that says, water is your friend. I refuse to call water a contaminant because it's always there. So, it's like having a constant enemy. So I consider water my friend. I just go ahead and I gently ask him to leave when I need to by using as much bake out as I can. The next one is, and I'm going to consider them together, carbon monoxide and carbon dioxide. I'm sure that if you look at your spectrum in your ultra-high vacuum system and you look at what's in there, you will see a peak at 28 and you'll see a peak at 44. Carbon monoxide and carbon dioxide come out of the filament. So once you turn on the filament and you heat it up, there is carbon in typically in the filament. Whether it's a thoriated filament or a tungsten filament, there is carbon in it. There is also water in the system, or in the case of an yttria filament, there is an oxide, and the carbon reacts with the oxygen, with the water, and it produces both carbon dioxide and carbon monoxide. So you will typically see a peak at 44, a peak at 28, and then you see the peak at 16. That's usually also methane from recombination that comes out of the carbon monoxide as well. Methane is a common fragment too that you'll see that will start outgassing in the system, and it's the first one you see, which is kind of a product of fragmentation and reduction of hydrocarbons that are in the ionizer. So literally, when you turn on your RGA for the first time, you can expect all these species to start coming up. And we haven't even touched on hydrocarbons yet. What you will also often see, the hydrocarbon peaks that start at about 43 AMU and go up as kind of like a soup of hydrocarbons. And I'll talk about that separately. So these are the typical background gases that you'll see in a spectrum. When you look for hydrocarbons by themselves, what you're going to find is that a system that has been, you didn't put gloves on, or you use alcohols to clean it, or it was, there's residual grease from oils, or from pump oils, or from diffusion pump oils, and so on. What you're going to find out is when you turn on the RGA for the same time and look at the spectrum, you're going to get this spectrum that has a cluster of peaks that almost look like electronic noise on the signal. And I have had units sent back to me claiming that there was an electronic noise problem when it was really this chemical noise problem. What you actually have here is these are clusters of fragments and different molecular weight compounds that are present in the system. And they come in little clusters of 14, separated by about 14 AMU. And the reason they are 14 AMU apart is because in a chain of hydrocarbons, right, every link, right, in an alkane type compound is a CH2, which is 14 AMU. So it's not unusual if you have long chain hydrocarbons to have peaks separated by 14 AMU, because the hydrocarbon fragments at every link, and it produces spectra at every 14 AMU, which are kind of identical to each other. So that's why hydrocarbons, you'll typically get this cluster of peaks, and they'll look like 43, right? You have a peak at 43, and you'll have, with a little cluster around it, there will be another peak at 57 with its own cluster, another at 71, and so on. When you see something like that, that means that your RGA has hydrocarbons in it, it's contaminated with organic compounds, and the way to get rid of them, of course, is to bake it out. So pump oil, plasticizers, very often you'll see them when you pull an RGA out of a packaging container where it got in contact with the plasticizers from the packaging. You put it on, they allow gas for a while, you bake it out, and eventually they go away because they have high vapor pressure. So those are typical background gases. You do need to know this table very well. Hydrogen, water, fluorine, which I show you a spectrum. Fluorine very often will become apparent in a spectrum if you work with fluorinated compounds. Like a lot of people use perfluorinated elastomers, perfluorinated vacuum greases, and so on in their systems. Those compounds, as they make their way into the quadrupole, into the ionizer, they fall apart, fluorine is released, and the fluorine then embeds itself into the ionizer, into the stainless steel. It's a very small atom, and it has a lot of affinity for stainless steel. So what happens then now, after that, every time you turn on the RGA, you will have a peak at 19 AMU, which wasn't there before. You will also see some of the vendors, when they clean the stainless steel and they do the degreasing process, they use perfluorinated compounds as well, and then the product will come to you and it'll have a 19 peak to start with. And of course, the 19 peak gets worse. The outgassing of fluorine gets worse when you turn the filament on. So, which is the reason why a person that was asking, no matter what I do, when I turn on my RGA, the pressure goes up. You will never get rid of that. By turning on the RGA, the temperature goes up. When the temperature goes up, the outgassing rate goes up. So whatever it is that was on the surfaces will start outgassing at a higher rate. You'll get a spike in pressure. You will also get these new compounds being formed at the ionizer, like carbon monoxide and carbon dioxide, and you'll be in big trouble. You'll have your pressure go up. I talk a little bit about EST as well. EST sometimes manifests itself also as part of the background spectra, and EST comes from ions being formed at the surface of the anode grid by electron bombardment. And you can often tell that they are different because they are ions with a lot of energy, and they show up as little shoulders on other peaks in the spectrum. So if you see this behavior where there is a little shoulder, that peak is not in your vacuum system, it's another background peak from the RGA itself. So here's a good example. I hope you can all see this very well of a, My system is not as good as the 5A-11 system, but, you know, one day maybe I'll have one like that. But right now, the best I can do in the system that I have here for R&D is typically about 5A-9. So if I run a spectrum on that system, this is what I end up with. And surprise, surprise, you know, the list includes all the usual suspects that I gave you before. There is hydrogen at 2 AMU, right, coming from the stainless steel, from the RGA itself, and from the rest of the chamber. There is water. Water is coming from everywhere, but most likely, if you got an increase in pressure in the system, it's coming from the areas adjacent to the filament that go hot, and now are outgassing at a higher rate. There is carbon monoxide and there is carbon dioxide as well. Where is that coming from? Well, there is carbon on the filament. The water is reacting with that carbon on the very hot filament and producing carbon monoxide and carbon dioxide. And then the peaks. And you can see here what I was talking about before. If you look at the CO2 peak, there is a peak before it at 43 AMU, right? And then there is, and so this is kind of like a cluster. And then there is another cluster at 55, right? Right here, starting at 55, 57 right there. That is the 14 AMU increase relative to the 43. And these are little clusters of hydrocarbons, right, at 14 AMU increments. And you will see them in vacuum systems that are contaminated with hydrocarbons. So what do I know about this system? Well, if I look at it, I say the spectrum is dominated by hydrogen. The only way this typically happens is in a UHV system, where hydrogen typically dominates. The second peak that I see is water, which typically in a UHV system, at 5-11, I bet you your water is about 5% of everything else. But there is water, and this will tell me whether I baked out my system enough. And then there is carbon monoxide and carbon dioxide. I typically ignore them unless they, you know, they're out of proportion. And then I can say in this system, I still have hydrocarbons. Can I live with this or not, or do I need to bake out my system? You know, do I bake out? So I made a lot of decisions just by taking one quick look at the spectrum, right? I can decide whether I need to bake it out to eliminate the water, to eliminate the hydrocarbons. I can look at my carbon monoxide and carbon dioxide, get an idea if the filament is doing okay, and I already know I'm at UHV condition. So when I was in grad school, right, I had the lab across the hall where I used to do some of the surface science experiments, had an RGA, and literally all I would do to know if my vacuum system was right was to walk by the door and look at the spectrum, and I would look at the hydrogen peak. If the spectrum was dominated by hydrogen, I knew my UHV was good. If the spectrum was not dominated by hydrogen, I knew I had a big problem. So one quick look gave me the answer. Okay, so this is my residual gas right at 5-9. What I have here now is what I did then is this is pretty useful. There are some RGAs that have what is called a background subtraction mode. So if I could, we're going to imagine is a system in which I turn on the RGA, right? I look at what the residual spectrum is. I take a look at this and I say, yeah, this is my standard system. I'm never going to get used to hydrogen, so I'm going to live with it. This is good, the normal amount of water. I'm not going to do any better. And I'm happy with all the other levels. And then what I'm going to do is I'm going to go ahead and connect that vacuum system to one of those calibrated leaks, and I'm going to go look at what's coming out of it. Obviously, when I open up the leak, right, I'm going to get new peaks, but the background peaks are going to be added to the spectrum. So if I take that calibrated leak with the helium and the on the argon, the new spectrum is going to look something like this. Now I'm a combination of the peaks that I had before, the background peaks, which are marked with P, and also the new peaks that I added, the helium, the argon, right? And of course, they are all present at the same time. So the question is there any way that I could separate one from the other? You know, is there any way that I could distinguish in my software what is background and what is real peaks? Well, one of the things that you could do is use what's called the background subtraction mode. In the background subtraction mode, what you do is you take this first spectrum, the one that we collected with no gas going into the chamber, and you save it in the computer memory. Then you open up your valve, you get all your new gases in, and then you tell the software to subtract one from the other. And when you subtract it from each other, voila, what you get is now helium and argon, and all the other peaks are gone. But notice, there's still a little bit of water on the spectrum. I was not able to subtract it completely, right? So what does that mean? Well, what this tells me in this case is that as the helium-argon mixture is coming in, it's bringing with it a little bit of water, right? And of course, you know, there's water in the stainless steel lines that I'm using to provide the helium, so it's very likely that that water is coming into the chamber and adding to the water that was already there in the background that was being measured by the RGA. So this is a great way to do background distinction. So not only do you need to learn to distinguish what are the background species in a system, but it's also very important to understand how to use these modes like the background subtraction mode. So what I'm going to do now, I hope that was clear. If it's not, you can always ask me questions. What I'm going to do now is going to give you some examples of background spectra that you can find in systems that are a little different. So let's take, for example, the spectrum that I have right here. This came right out of the AVS monograph, and we use this all the time. This is a residual gas spectrum. It's a UHV system. It's a 1E-9, but this system was being pumped with an ion pump. And when the guy turned on the user, right, the tool owner or whatever, the vacuum system owner turned on the RGA, he got this spectrum. So what do you see here? Okay, they're not showing us hydrogen, right? But clearly the spectrum is dominated by this 18 AMU peak, which is water. And I expect to have water in the system. But there is a new peak here, a 20 and a 22. And of course you have the 28 and the 44, which I'm always going to get because the filament will always outgas carbon monoxide and carbon dioxide. I don't care what filament you got. So in this case, what we see is 20 and 22. And you might ask yourself, what is this? Well, this happens to be an ion pump system. And ion pumps don't do a good job with noble gases unless you buy a special version of it. So in this case, what's happening is this system has been pumping for a long time. It might have been exposed to neon at some point, and then after it got exposed to neon, or maybe it was exposed to air for a long time, right? Now neon is outgassing from the pump itself, and in this particular case, you are going to have to, with an ion pump, you're going to have to add to your list of usual suspects 20 and 22. They're always going to be there in your background spectrum. So they become part of your everyday operation. So a little bit more on carbon monoxide and carbon dioxide that is very, very important. And it is that every day when you turn on your RGA, I'm going to keep picking on this 5-11 system, right? You turn on the RGA, the pressure in the system goes up, which obviously means that material is outgassing. You're going to go run the RGA, and you're going to get a spectrum. And I will pretty much assure you that you will see a peak at 28 and a peak at 44 AMU corresponding to carbon monoxide and carbon dioxide coming out of the filament. Okay? So you will use that to say, okay, things are normal, everything is going well. What you got to realize is that ratio of carbon monoxide and carbon dioxide will vary as time goes by, and also depending on the amount of water in your system. So in other words, if your filament ages, you're going to expect to see a change in the ratio of 44 to 28. So what that means is that if you're going to rely on the background subtraction method, you're going to have to keep changing your background, routinely. The other thing that's going to happen too is your amount of carbon dioxide and carbon monoxide will also be related to the amount of water that is in the vacuum system. So in other words, if I added a little bit of more water to this system here, most likely the carbon monoxide and carbon dioxide peaks would go up relative to they were last time. Okay? The reason that's happening is because I have more oxygen available to react with the carbon that is on the filament, and I form more carbon monoxide and carbon dioxide. And I'll give you an interesting story. I had a friend of mine, he detects carbon dioxide emissions at the bottom of the ocean. And he was doing some studies where it was a sulfur emitting place, and he took an RGA down there in a submarine, and he turned on the RGA and he realized that there was carbon dioxide on his spectrum. And he didn't know this rule about, you know, what the residual gases are. He was kind of new to the methodology. And so he wrote a paper saying that for the first time he had observed carbon dioxide emission from these, you know, these fumaroles at the bottom of the ocean in this place. And then he sent me a copy of the paper because he's a friend of mine. And I had to ask him, well, was there a lot of water in your spectrum? He goes, yes. So he had to write a retraction to the paper as a result of that. So the moral to the story, though, is that very often when you look at a spectrum and you look at the background signals or even the regular signal you're seeing, some of the peaks are going to come from the interaction of the different chemical species that are in the system with the filament, with each other, and creating peaks that you won't necessarily expect, but that can always be explained in terms of chemistry. So in this case, changing the level of water in the ionizer, even though it should only change the water levels, it also affects the levels of carbon monoxide and carbon dioxide. So always keep your chemistry mind open, okay? Because these things happen all the time. In terms of the list of usual suspects that we have, if you're UHV person, your spectrum will most likely be dominated by hydrogen. If you're not, if you're a regular vacuum person, you know, typical 10 to the minus 6, you know, 10 to the minus 7, 10 to the minus 5 torr, minimum pressure, and you're doing a residual gas analysis on that, water will most likely be your dominant gas. And water is going to, the outgassing of water was going to limit your ability to achieve a target pressure. So I cannot emphasize how important it is to have an RGA in a vacuum system where you rely on hitting target pressures every day. If this were my vacuum system, right, I would, every day, I would bake it out, right, overnight. I would come in the morning, and I would look, turn on the RGA and look at what my signal looks like. If my total pressure hasn't achieved its target pressure, and look at the spectrum, and even if the spectrum, I don't know that it's perfectly calibrated, is completely dominated by water, I know for sure that the only way I'm going to achieve the target pressure is by baking it out. On the other hand, if I turn this on, and what I saw was a big peak, you know, a nitrogen peak and an oxygen peak, and we'll talk about that in a minute, then what I would know is that I have a leak. And in that case, I can bake out my system for the rest of my life, and I will never get to where I need to get for a target pressure. Okay? So, one more example. This is a spectrum I got in my vacuum system, right? Hydrogen dominates the spectrum in baked UHV systems. What you're going to find out, too, is if you keep your RGA on, right, when you baking out a UHV system, the hydrogen signal is going to go crazy on you. So ignore that. It's hydrogen coming out of the stainless steel. It's perfectly normal. There is nothing wrong with the RGA. It's what is to be expected, and the RGA is just measuring. And I will tell you one thing for sure. So if you look at the spectrum right here, right, I have a total pressure gauge in this system, and the total pressure gauge said 1E-9 torr. But if you look at the hydrogen peak, right, in the spectrum, and I don't know if you can read that on the WebEx thing, it says about 1.5E-8 torr. So I will always get calls for RGAs from people asking me, wait a minute, my RGA, my total pressure gauge says 1E-9 torr, but your RGA says that I have 1E-8 torr of hydrogen. How can that possibly be? You know, which one is real? Am I at 1E-9 or am I at 1E-8? The thing you have to realize is that this number that the RGA is providing is artificially inflated by the fact that it is overestimating the amount of hydrogen. So remember what I told you before. RGAs overestimate the low masses and underestimate the high masses. So hydrogen, not only does it outgas locally right at the ionizer, it also gets overestimated by the RGA. So the only way that you could possibly have this device give you a proper hydrogen level is if you had calibrated the amplitude of the hydrogen peak to hydrogen. No other way to do it. So keep that in mind. RGAs, particularly on UHV systems, will not agree with the total pressure gauge. They will always overestimate the amount of hydrogen. The reason they do that is because it's a double whammy of hydrogen outgassing right at the ionizer and the RGA overestimating the amount of hydrogen. Okay? I'm going to give you one more example of a cross interaction between species. This is a vacuum system with a titanium sublimation pump, right? So, you know, not too many people use these pumps, but in a titanium sublimation pump, you literally take a rod of titanium, you heat it up really, really high temperature, and you sublime the titanium, and the fresh surface of titanium acts as a pump, and then stuff deposits on it, and then a new layer of titanium falls on it. Well, what's happening in this case? In this case, what's happening is this particular system here had an air leak, which I can tell because there is a peak at 28 and a peak at 32 AMU, and we'll talk a little bit more about this. But so this 28 peak and this 32 AMU peak tell me that I have air coming into the system, okay? But remember, the 28 peak is nitrogen, which is N2, and the 32 peak is oxygen, which is at 32 AMU. So N2 plus, O2 plus. I also have a peak at 30 AMU. Where is that peak coming from, right? So when you look at the spectrum, you might be surprised to find a 30 AMU peak, which when you look it up, right, you might figure out that maybe it's NO plus. So what is happening in this case? The nitrogen and the oxygen that are going into the system are reacting with the incandescent titanium, right, breaking apart into nitrogen and oxygen atoms and recombining to form nitric oxide, NO. That NO then is getting to the RGA and getting detected. So that's why every time that air comes in, right, nitrogen oxide are present, also 30 AMU comes out. And you might say, well, what does that have to do with my RGA? The same thing happens in the filament of a residual gas analyzer. If air comes into an RGA and you make ions of nitrogen and ions of oxygen, you will always have a peak at 30 AMU as well, which comes from the nitrogen and the oxygen reacting with the filament and forming nitric oxide. So you can actually see it right here. We're going to talk a little bit about air leaks, right? And this is what shows you how powerful an RGA can be. Here's an example of an air leak. So I have a vacuum system. I close the gas delivery valve. I open up to the pump, and I let it pump overnight. I come in next morning, right? And I'm not at my target pressure. I did not achieve the pressure that I wanted. I run a quick scan on it, and I get the spectrum that is right here on the screen. So what do I see? I see two things. You know, if it were me looking at this spectrum, I would look at the spectrum and say, all right, what do I see? I see a peak here at 18 AMU and at 17 AMU. This is water, right? And I say, okay, this water is 5 E minus 9, and I'm shooting for a 7 E minus 9. This water is good enough. I don't need to bake out my system. But then I look over here and I find there is a peak at 28 and there is a peak at 30 AMU. And they're roughly at a 1:4 ratio, right? What this tells me is that the reason my system is now pumping down is because I have an air leak. Something is leaking, a valve, an O-ring, a gasket, you know, something I did is messed up. And now I have air coming into the system, and that needs to be fixed. If I remove the leak, right, these two peaks will be gone, my total pressure will be dominated now for the water, and I will most likely make my target pressure, and I'll be off to the races. Without this information, I will be sitting in front of the vacuum system wondering, I wonder if I have a leak, or I wonder if I have, too much outgassing of water inside the system. So your options would be to pull up a leak detector, a very lengthy process to go and leak check the system, or bake out the system for a few hours and see if the signal goes down, right, below the the detection limit, which might not happen because this might be as good as this system gets. So one quick look at an RGA scan after an overnight bakeout, or overnight pump down where I was trying to hit a base pressure, it will tell me immediately what is wrong with the system, and it will tell me what to do with it. Okay? So the other thing that I want to mention to you regarding air is that when you look at this air spectrum, and I'll mention one more thing. If you actually look at 30 right here, right, that little shoulder right there, that's the NO peak that comes from nitrogen and oxygen reacting at the filament. So it's not like you have a 30 AMU molecule coming out of your vacuum system. No, there's air coming in and the air is forming NO. So you don't need to worry about this guy. Once you remove the water, that peak will go with them if you're worried about nitric oxide. But so this scale right here, if you look at this scan, right, the scale is in linear mode. So in other words, a linear scale. If I take a air spectrum and I use a logarithmic scale, things look a lot more interesting. And what you'll actually see is that now I can actually see the peak at 28 AMU, right there. There is a peak at 32 AMU. Here's your 30 peak again. And then there is a peak at 40 AMU, which is the naturally abundant argon in air, right? And there is some also CO2, which is the naturally abundant CO2 in air. So here's my trick that I usually do. If I go turn on, I baked out a system or I pumped down a system overnight, I come in the morning and I look at it and I go, okay, there's a peak at 28 and 32. This could be air, right, in the coming into the system. If the leak is big enough, then I always go and look to see if there is a 40 peak as well. If you see the 28, the 32, and the 40, and the ratios agree with what you're seeing in this graph, which you can pull out of the NIST library, you can take it to the bank that there is an air leak in that system. So very often, people will tell me in the lab, I think I have a leak. I'll go, do an RGA scan. So they'll do the RGA scan. Say, do you see nitrogen and oxygen? They go, yeah, I do. Say, are they in the right ratio? They say, I think so. And then, the 4-to-1 ratio. I think so. I said, do you see argon? Particularly if this is a system where we never put argon in it, he goes, yes. I said, you got an air leak. Done. It's solved. So what that means is at that point, you use the same RGA now. You don't turn it off. You bring some helium, and you leak check the system, and you start looking at mass 4, and you debug your leak right there in front of the vacuum system. You can do that with an RGA, and this is the only reason why I say you should never build a vacuum system without an RGA in it. All right, so I think here I have a few examples. We talked a little about this. This is nitrogen coming from, this standard nitrogen spectrum. We talked a little about this. Nitrogen has a parent peak at 20 AMU, and then there is a little fragment peak at 14 AMU, typically between 7 and 10%. This is what you use, right? Remember, there is also carbon monoxide coming out of the filaments in an RGA. So sometimes the question arises, well, I'm seeing 28. Is it carbon monoxide from the filament, or is it nitrogen coming in? Well, look at the peak at 14 AMU, right? If the peak at 14 AMU is 1/10 of the peak at 28, it's nitrogen. If the peak at 14 AMU is not there, obviously it's not. You must look for 12 and 16, and that must be carbon dioxide. So you very quickly diagnose your system. And again, it's always good to know what spectra look like in a log scale. If you look at nitrogen in a log scale, there is also a peak at 29 AMU, which is the peak that comes from nitrogen 14 and nitrogen 15. And I often use these two peaks to make sure that the mass spec is working well, to make sure they get well resolved. I use it as a diagnostic. Okay. So that pretty much kind of walked us through all the typical background gases that you have in a spectrum. And I kind of show you that what's going to happen is if you pump out your system and you pump and bake out your system, you'll typically go to a spectrum that looks something like this with the usual suspects. And then when you add your gases, you add your samples or whatever it is, they will go on top of that. The partial pressures are additive. And as long as you know what your background spectrum looks like, you get used to it, you can subtract that background spectrum from the gases coming in. Always be careful though, and keep in mind that sometimes whatever you put in might react with the RGA, and it might change the background spectrum a little bit by chemical reactions. So put the chemist hat on and think about whether anything that you put in could actually be affecting the background as well, which could affect your quantization. And I talk a lot more about that in the long course, but we don't have time for that today. So moving forward, what I have is, now we get away from the standard, background spectra, stuff that you will have even if you're super careful, right? And we're gonna look at a few examples of other molecules. It's very common in the semiconductor industry to wipe your system with isopropyl alcohol. It's kind of a kit clean process. You just go wipe everything up, you dry it, then you pump on it. Well, once you start looking at alcohols, right, things start to get a little more complicated because this is an organic molecule and it's going to start fragmenting. So here's an example of isopropyl alcohol. And I cannot tell you how many times I've gotten from a customer they'll send me there is some problem with a total pressure gauge or something like that is failing. And I ask for an RGA spectrum and I get it back and it looks exactly like this, IPA. And a quick look at the spectrum, if I can match these 5 peaks, right, 45, right, look, there is a 43 here, which could be hydrocarbons, but you have these 2 guys here that help you separate, right? If I get all these peaks all at once and they are approximately the same ratio, you know for sure that you have IPA in your spectrum. Silane, and the reason I have it here, silane is fairly common, right? Variety of applications, from epitaxial growth of silicon to, you name it, anything has to do with silicon. Complicated spectrum, right? Lots of peaks, easy to identify. The thing that you have to be very careful with silane, though, is that this is a perfect example where chemical reactivity is going to get in the way. And what happens is the silane will react at the filament, as you can see it right here, and it will decompose completely until it produces pure silicon. That silicon now can react with the oxygen on the filament and start to form silicon dioxide. So literally, if you're going to be operating in silane, get prepared and order a lot of ionizers, because what's going to happen is your ionizer will get coated with essentially sand, SiO2. And you're going to look at it, you're going to have like a bluish tint, and it will work for a while, but as soon as the whole thing gets coated, it will lose its sensitivity completely. So that's the other thing that you have to keep in mind, which is that once you identify species in the RGA, it's good to know what things work with the RGA and what things don't. And silane is a perfect example that will kill both the ionizer. Unfortunately, it will also kill electromultipliers like crazy. Okay? Going up the scale, this is TIOS, right? Very common, also organic compound used in semiconductor, very complicated spectrum. This guy will kill your RGA in no time. Easy to identify, right, from the spectra. You can get this right out of the NIST library. One more thing I'm going to mention. I think we're getting to the last few minutes. Then we're gonna take questions, right? I'm going to mention a couple things that are pretty important. And the one is, I don't know how many of you do processes, but if you do thin film coats, PVD, CVD, it's very likely there is argon in your system. The thing you have to keep in mind about argon is that whereas the argon at 40 AMU is the main peak in the spectrum, argon has isotopes. And it has an isotope at, so the main isotope, the most abundant one, is at 40 AMU. It has an isotope at 38, and it has an isotope at 36. Okay? So here's the, and you can see, right, if you, argon will not, with 70 EV electrons, will also doubly ionize, and it will form argon 2+ ions, which show up at 20, 19, and 18 AMU. So if in your system you're trying to detect water and try to measure how much water is left in the system, if you have argon present in the system, there will be a background of argon 2+ on top of that. So you got to be very careful when you look for water at 18 AMU in an argon system, because what you think is water might be argon doubly ionized at 18 AMU. Here's the good news. It's very possible to eliminate these peaks from the spectrum. If you go ahead and you reduce the electron energy from 70 eV to 35 eV to 35 volts, from 70 volts to 35 volts, what's going to happen is the argon will continue to singly ionize, but it will not doubly ionize. But water will continue to ionize. So if at any point you're running argon and the argon doubly ionized 36 is getting in the way of you measuring water levels in your system, residual water levels, just lower the emission current to 35, your doubly ionized argon plus will go away, and you'll be able to look at water directly. This is a very important trick, and if you look, in fact, at some of the closed ion source systems or even standard RGAs, you're going to find out that sometimes they advertise that they have the 35 EV mode. The purpose of the 35 EV mode is there to allow people to do water measurements in the presence of argon. Okay? So we can go on like this with different examples of interactions, right? And different ways in which different gases can interact with each other. But I honestly believe that for you to start using an RGA and be successful with it, the trick is know your background gases in your RGA. They will be different for every RGA. They will change over time. They will depend on the history of the RGA. Somebody borrowed it, comes back to you, it will change. But know what that is. You know, do it at least once. Figure out what that spectrum looks like. Print it out and put it on the wall as a poster so you know what your system looks like. You know, and update that poster maybe once a month or so on. And then anything else that you add into the system, right, is the only stuff that is real is the stuff that is real relative to that background. Subtracting that background spectrum that you know about. If you can, use the background subtraction mode if it's available in the code. If it's not, save the spectrum and subtract them yourself. Yep, right? It's another way to do it. But if you know that, you are way, way ahead of the game. And the other thing, of course, to keep in mind then is the next step of sophistication is understand how things react with each other at the hot filament, so you understand which peaks are really just a manifestation of a crosstalk, and also understand things like this argon thing. How does double ionization overlap with the peaks that I want to see, and so on. How fragments work, and so on. Okay? And for that, and I think we are kind of at the end here, and this is a very good spot. What I will tell you is, it's the first time that I went to an AVS show, and I won't even say how long ago that was. I don't even want to remember how long that was. I went in and I showed up with a brand new RGA, and I was showing spectra with all the peaks in a log scale. So when I mean a log scale, I mean the y-axis, right? The pressures are in a logarithmic scale. We're in the x-axis, we're still in the linear scale of AMUs. And people will stop by and ask me, what is that? What are you showing me? Because people were used to what's here at the bottom, which is the linear type of display, which used to be the standard way of displaying spectra. There is a lot more information you can have in a log scale. You know, look at all the information that is in the upper plot relative to the bottom plot, right? And if you really leave your RGA running in linear mode, you're losing all that information in real time. And the good news is that, you know, many, many years later, now everybody does this, right? And you can always go and set your scale to linear mode if you want. But my recommendation is, particularly for heating-based pressures, is keep the log mode on, because very often the problem is hidden in the little peaks, right? If there is some problem, there is a building problem in your system, it's going to show up at the bottom of the scan, and then sooner or later it's going to go above, you know, your detection limit, right, where you care, and you'd rather know sooner than later. So by all means, always use log scale. And this brings me to this slide, which is, where do you go and get spectra? My main source of spectra is the NIST webbook, and the NIST webbook is great. You can literally enter the mass of a peak and it will suggest species for it. Or if you think you know what species it is, you can type the formula. It will give you the mass spectrum and you can compare. So here's a good example, right? So that's one way to do it. And the other possibility is a lot of the software that you buy nowadays will also come with a library. And that library will includes, common species that are found in people's applications. So here's a good example, right? A vacuum system. It's on the left side. It's a water peak right there. The typical carbon monoxide peaks and so on. But here you have these little clusters separated by 14 AMU. I looked at that and I said, this is most likely oil, right? This repetitive pattern every 14 AMU, most likely oil peaks. So what I did was I went into the library and said, show me the spectrum for pump oil, for standard pump oil. You bring it up, and sure enough, the peaks completely overlap, over the range that I measured. I would call this a match. I would say with certainty that these peaks are oil. And, and I could have done something similar going here, right, except that I would have done a lot more hits. But more than one way to actually do spectral identification. There are lots of tables out there and so on that you can use. And this is a good one with a lot of different species that people use in their vacuum system. So I hope that this kind of gave you kind of a spectral identification 101 methodology. Everything I'm telling you here, that I told you here, is exactly the way I think about this. There's no secrets that I'm keeping for myself other than those that I'm running out of time to tell you. This is exactly how I operate. Buy the RGA, I mount it, I pump it down, I bake it out, I characterize the residual gases, I make a poster of it, I put it on the wall, and whether you do it for real or virtual in your head doesn't matter, or you save it on the screen as a screen dump, or you save the spectrum, and then after that, every time that I put something else in, right, I compare to that background spectrum. Whatever wasn't there before, that's the new stuff, and I do the math on that. And that's all there. And then in terms of, okay, now I found peaks that were not there before, how do I know what they are? You go use the spectral library in the software, you go to the NIST web library, or you use a table, and you start doing spectral identification. And while you're doing spectral identification, if there are peaks that you don't know what it is, you start thinking about fragments, you start thinking about double ionization and so on, and soon enough, you identified every peak in the spectrum. And I cannot do this for you. You have to do it, but I'll tell you, you do this a few times and it will become like duck soup for you. I guarantee you. So, what do you think, Keith?
Yes, I'm sorry?
What do you think? Should we go to questions or?
Well, if you want, you can go until 5, and then
we'll go till 5 and do 15 minutes of.
Yeah.
Okay, perfect. So this is one. If you have any questions about what we just talked, let me know. So what I'll do is we'll finish, which is what I was hoping that I was going to be able to do. Is I'm going to back up a little bit, and I'm going to give you a few pointers. I don't know how many of you operate in residual gas mode, how many of you operate, as residual gas analysis, how many of you operate as process analyzers, but I wanted to kind of walk you through these a little bit. So let's talk about process sampling, okay? So everything we've talked about so far was the case in which we take the RGA and we connect it directly to the vacuum system. The RGA is immersed directly there. And that's all great as long as the pressure of gas never exceeds 10 to the minus 4 torr, right, which is the maximum pressure that is allowed. Unless you have a miniature, you can go to 10 minus 2, sure. But so what happens if you want to analyze the gas in a chamber that is going to go higher than that? It's going to, you're going to do a PVD process at 10 to the minus 2 torr, or a CVD process at a torr, or an ALD process at even higher pressures. And you want to know what the gas composition in that system is. What you're going to have to do in that case, you're going to have to develop a system that is a little more complicated, that is a process sampler. Okay? So this is what I want to tell you. It doesn't matter how much I explain this to you, I will never be able to provide you as much information as you're going to get out of this paper, the recommended practice for process sampling for partial pressure analysis, which was another effort. It took 13 years to put together all this information. It pretty much, every trick that is known is in this paper, how to sample at higher pressures. So if anything, just write this down, get the paper, keep it in your filing cabinet, and if you ever have to do high pressure sampling, this is where you go. You don't have to remember anything I told you today. I promise you it will all be there. So the question is, what if I have to sample at a pressure greater than 10 to the minus 4 torr? Well, in that case, your first option is to use what is called a single-stage differentially pumped system. In that case, what you're going to need to buy is not just an RGA itself, but you're going to have to either buy or put together a differentially pumped system, which what it's going to do is going to connect to your application system, right, to your whatever your process is, and then it's going to, through a valve, right, on an aperture, it's going to connect to another chamber which has its own dedicated turbo pump system and the RGA in it. So during normal operation, this is what's going to happen. Here's your main chamber, right? What's going to happen is, if you're doing a regular base out, you will just open a high conductivity valve, which is this valve right here, and you'll just use the RGA as usual. You'll open up this valve, the gas will go in, and you'll be able to know what your base pressure is. As soon as the process starts, you will close this valve, right, which is this valve right here, and you will open another valve which leads through an aperture to the vacuum system. So what's going to happen is the pressure is going to be stepped from whatever your process pressure is, 10 to the minus 2, down to a pressure that now the RGA can use. It's called a differentially pumped system. And if you call a vendor and you say, I want to sample gas, they're going to tell you at what pressure, and they will put all this together for you so that you are able to sample gas at whatever pressure your process is, maximum of about a torr with this configuration. And you'll be able to use the RGA to measure pressures of higher gases than 10 to the minus 4 torr. So the other option is, if you don't want to spend the extra money that it takes for a vendor to put it together, you can go ahead and read the paper, right? This paper, and it will tell you how to do this on your own, how to do all the calculations, you know, what sample orifice diameter to use, and so on, and you'll be able to put your own system together. The main thing when you buy one of these systems, the differentially pumped system, what you want to look at is, as far as specifications are concerned, what kind of pumps do they use? You want dry pumps, you want at least 40 liters per second on the pumping speed. The other thing that you're looking for is, what is the gas flow? And here's a good example, the response time. In this case, they're telling you it will take 2 seconds, right, at 0.1 millibar inlet pressure for response. And what it means is that if your pressure goes up, right, by 0.1 millibar, it's going to take 2 seconds for the system to respond. Okay? So there's a response time that goes along with it. This might be okay for you or not. And the way you change that is by changing the pumping system and the diameter of the orifice. The other thing you got to look at is, what is the gas flow into the system? Because you got to realize, if you're using this to, for example, sample a seal volume, this is constantly removing gas from your system. So you got to be careful that it doesn't deplete the gas that is in your sample. So that's, you know, you start measuring and you go, hey, my pressure keeps dropping all the time, and maybe it's dropping because the flow into the system, even through the sample aperture, might be higher than what your system can actually handle. Okay? So that is the differentially pumped system. I didn't see any questions on closed ion. There is another kind of source, by the way, that is also available, which is a closed ion source. And what you're going to find out is that if you ever call a vendor to buy a process system, a process analysis system, anything higher than 10 to the minus 4 torr, the first thing they're going to want to do is sell you a closed ion source system. And they're doing it for two reasons. They're doing one because they can make more money at the closed ion source system. So, this is a sales guy, you can't blame him for it. But the other reason he's doing it is because it has a better detection limit for water. Okay? So if water level measurements down to a part per million are very important for you, definitely order the closed ion source version. But I will tell you right now, closed ion sources are higher maintenance devices. Filaments break a lot more, the source gets contaminated a lot more, they require a lot more hand-holding that open ion sources do. So when you start looking at differentially pumped systems, and the paper, by the way, the publication that I mentioned to you will help you make this decision as well. They will push for the closed ion source. You don't have to do it. There is very good reasons, and there are papers out there. There's one good publication in the SRS, the Stanford Research Systems RGA website that gives you the advantages and disadvantages of the closed ion source versus the open ion source. Okay. One thing I was going to mention too. Keep in mind too that most vendors, if you're a person that does a process, but you do a physical vapor deposition or chemical vapor deposition, very often you can look into their catalogs and they'll have process systems put together specifically for your application to handle the kind of corrosive gases or pressure ranges or whatever it is that workflow that you do in your application. So whenever one of these is available, I would highly recommend that you go with it and you tailor it to your application by talking to the vendor, right? So the last thing I want to mention, and I think then we're going to be done, and this is perfect because this covers everything that I wanted to mention, leaving you extra notes, if you're curious, is what if you want to sample gases at atmospheric pressure? RGAs can be used to sample gas composition at atmospheric pressure, and in that case, what is typically done is they are connected into what is called a bypass pumping system. And the idea is that, here's a couple different products that are available in the market. The idea here is very simple. In this case, you have gas at atmospheric pressure that is coming in. It goes in through a capillary, and then there is a mechanical pump, right, that pumps on the capillary and brings the gas in this pattern. So the pressure drops, on this side of the capillary. So you're able to bring in the gas from the atmospheric side, pump it down to a lower pressure. Then that gas is sampled through another aperture into a residual gas analyzer, which is being pumped by an RGA. So even though the pressure here is atmosphere, by the time you get here is about 1/10 of a torr, by the time you get here is about 10 to the minus 6 torr. And now the RGA can sample it. And since the gas is moving really, really fast in front of the aperture, you have a lot of speed. So if you want to measure any gas composition above 10 torr, this is what I recommend that you do as a sampling system. And of course, once we go on the RGA side and it comes to looking at the spectra and all that, the same exact rules apply. You will always have a background spectrum, and in this system, right? When you close all the valves, and when you add the gas, you will have to subtract the background spectrum from the gases that you're bringing in. The background spectrum will have the usual suspects because most of them will ask you to degas the RGA or to bake out the RGA during the process. So it's kind of the same rules apply. The only thing that changes is that you have this pumping system in the front end of it that will allow you to bring the pressure down to a value that is compatible with the RGA. So with that, I think I've covered everything that I think we can humanly cover in 4 hours. There is a lot more that you can get from the full course, but, we only have 4 hours, so there's where we are. And I hope this was useful to you. So I think we should probably go to questions now, right?
Yes, that sounds great.
So let's see.
Hi, yes, I have a question.
Great.
Can you hear me okay?
Yeah, great.
Okay, so typically we use our RGA for trying to troubleshoot chamber issues and eliminate contaminants and all that. But I was wondering, would it be inappropriate to use it with having a chamber and purposefully introducing like hydrocarbons, oils, to analyze at what level of vacuum that they individually would vaporize? Would that like immediately contaminate the ionizer and like ruin the RGA? Or is there another type of sensor that would be better for something like that?
Right. No, I mean, realistically, right, what are your choices other than doing, particularly, is your end goal to then use the RGA to do analysis later on, to characterize those pieces, like you're trying to create a library of your gases to know later on how to identify them?
Yeah. Try to catalog them and identify at what stage that they individually react.
Yeah. So this is why, if it were me doing it, right? You gotta create your library. You don't have a choice, right?
Right.
You will introduce the hydrocarbons, and I guarantee you that after a while you're going to start seeing degradation. There's no choice there, right?
Right.
But here's the deal. So if you keep your pressures low in the 10 to the minus 6 and under, right, and you use the RGA to sample, you will get a spectrum. You don't need to, you just need to collect the spectrum and move on, right? And by the way, every single time you kind of want to know what your background is so you can subtract it, right?
Right.
And then what I would do is, it's inevitable. Eventually you will start degrading, right? But the general shape of the spectrum, right, will not change. So even if the spectrum starts to lose sensitivity over time, right? And I'll tell you, even if it loses sensitivity by a factor of 10, right? Because because it gets coated. As long as your background doesn't look, like it has a lot of peaks that are going to bother you, you can continue collecting spectrum, right? Baking out every night, cleaning it up every night, but you can continue collecting spectra until you finally, you realize, I have nothing left here. And I do that all the time. So it's inappropriate, in the fundamental thinking of I want my RGA to be as pristine as it can be. But the reality is your RGAs will never be pristine because you're going to use them to look at hydrocarbons anyways. So, this is one of those cases where go ahead and do it. Keep the gas concentration. So you'll probably put your sample, you heat it up, you'll get your vapor pressure, you'll collect your scan, right? Save it. And then, pump it out so that it's all out of there. You go back to background spectra. That might mean baking it out or whatever it is. And then you're going to do it again, and you're going to keep doing it. And in between, you can introduce a little bit of nitrogen, right, to a known pressure in your ion gauge and make sure that you're not losing a lot of sensitivity, right? And I have that. Like the RGA that I have in my lab right now started with a sensitivity of 2.2 E minus 4, right? And right now I'm at about, something like 5 E minus 5. And doesn't mean that I'm going to take it apart or do anything exceptional. I just recalibrate the sensitivity and life goes on because I don't need the sensitivity at the low end, right?
Right, because you know what you're looking at. Right.
As long as you're not so far contaminated that you can't see the small stuff that you're interested in, who cares, right? And you got to be practical. So, I hope that helps.
Yeah, absolutely. Thank you so much.
Oh, you bet.
Okay. This is Vadim. Can I ask a question?
Sure.
We are going to use RGA, in order to characterize the parts before we can ship them to our customer, so they're clean.
Yeah.
And basically, all I need to do is measure organic compounds and water. But before that, I hook up RGA to the furnace in which I bake the parts.
Yes.
I bake the parts in hydrogen, then I close hydrogen, pump down to vacuum, open the valve, turn on RGA and measure, right?
Yes.
So my question is this. Once I evacuate the furnace and it's high vacuum, the parts may be still warm. I mean, there is vacuum, so all I have is radiance. And the RGA is on the exhaust manifold, so there is no direct radiance to RGA.
Yeah.
Basically, how long do I have to wait down to what kind of temperature before, or is it even important because RGA is not going to see the radiance?
Right. So yeah, that's the answer, right? So the particularly if it's out of the line of sight, right? If it's all just infrared, right, radiative loss, right, from the surfaces, no big deal. The only thing that you have to worry about, right, in this case is the first one is while the RGA is sitting, do you isolate it when you heat it? You're doing all the heating and all that? Okay.
Yes.
What you want to do
I do it in hydrogen, so it's isolated. Perfect. I have a valve.
Beautiful. Yeah, so that should clean it. The only thing you got to worry about is that, you know, while it's not being used, right, that you keep it under vacuum, that you bake it out, right, so that whatever it was exposed to last time is good, and that you get a nice background spectrum to figure out, you know, where you are. And the other one is make sure that it doesn't that the electronics do not get hot. So 2 rules of thumb, right? If you use an electromultiplier, you cannot operate above 100 C. So if your probe is higher than 100 C, you cannot operate the electromultiplier.
No, I'm not going to use a multiplier.
Okay. So then the next. Yeah. Go ahead.
What I'm going to do is every once in a while I'll just bake the empty furnace without parts.
Yes.
And measure the background.
Perfect.
Do the same kind of process without the parts, but the furnace itself is basically very susceptible to, contamination. Heat shields or heaters, there is a lot of spaces to collect stuff.
Right, and you put the parts, right, you're obviously checking them because you don't know if they're clean, and if they're not, the stuff has to go somewhere, right?
Well, I wash them. Basically, the baking hydrogen is to remove the oxide films.
Oh, okay.
We're baking refractory metals like molybdenum and stuff.
Okay, all right.
They oxidize in the air.
The oxygen by turning into water, right?
Mm-hmm. Yep.
And then, so how do you look at total hydrocarbon, total organic? Do you look about 45 AMU for organic content?
I don't know yet. I'm about to build that system.
Yeah. So there is a lot in the literature about this, particularly for the level of cleanliness that you're going to be looking at. It's very, very common to do what's called a total organic content. And what people will do is they will add, right, in your case, you do a background scan in your chamber, like you said. You make sure there are no hydrocarbons, or you figure out how much hydrocarbon there is. Then when you run your parts, you essentially add the amount of signal from all the peaks above 45 AMU, and that's what they call the total organic content, right?
Well, I need to give them 2 outputs, like long chain and short chain. So I need to break it into two halves, right?
Okay. And how are you going to do that?
I don't remember, but there is a spec. I think
it's a spec. Okay, right.
Right, because I have to get like a 200 atomic units RGA and measure all the way up there.
Oh, okay. So you're probably breaking the range into 2, is what it is.
Yeah,
right?
I think it's 45 to 90 and then above 90 or something. Yes,
that's very common. That's high energy physics labs. If you look at their specs, they do this all the time. So it will work. It will work. And if you baseline you get your background every time on the chamber by itself. It's like I said before. You almost want to have a poster on the wall, right? To show you where you're starting.
We have time for one more question.
Thank you.
Great.
This will be your last. Anyone?
So
I've got a real quick question.
Okay.
We have a Henning gauge, co-cathode gauge, connected to our a little test setup, and I just read that that's a no-no to be in close proximity to the RGA. What do you recommend relative?
I get that one all the time. So here's the deal with that. So the penning gauge, right, has a magnet in it, and it's a pretty strong magnet. They're usually about 1 kilogauss, right, on them. The first thing that I will look at is which one are you using? Do you know what model you have?
A model of penning gauge?
Yeah.
Not up. I'm looking at it, but I can't. It's 8 feet away. I can't read it. Should I go look for the model?
You can, but I'll tell you how this goes. There are units that have higher external magnetic field than others, right? So here's how I do it. The magnet only affects the electrons in the RGA. And this is why kind of knowing how the RGA works is important, right? So there are electrons only in 2 places in the RGA, in the ionizer region and in the detector region, okay? So this is what I'll tell you, this is as simple as this. This is what I would do. You get your vacuum system, take the penning gauge off, right? Put a blank on it. And then fire up the vacuum system, fire up the RGA, and start collecting a spectrum, right? And then once you got your first, background spectrum, grab the gauge, right, the penning gauge, and put it, kind of put it right where you think you're going to put it, right? And see if the spectrum changes. Okay?
Yeah, okay. So the magnet just comes off with one screw. You can just pull the magnet right off, so I don't have to.
You don't even have to do that.
A blank flange.
Beautiful. So you remove the magnet. If you don't see any change in the spectrum, right, then you're done. So there is no residual effect or anything like that. Either the magnet is affecting the trajectory of the electrons or it is not. This is not like something that builds up over time or you're going to magnetize the RGA or, nothing like that. It either is affecting it or it is not. Now, let's just say that you remove the magnet and you do have a problem, right? So what will you do? If you do that, then I would take the gauge and I would put a elbow and I would put the magnet at 90 degrees, right? Because which way you affect the electrons also matters. And I have people that, literally put an elbow and then they start rotating it around, right? And eventually find an angle where nothing matters.
Okay. Yeah, I see the whole picture and I see exactly what we can try to do because it's a pretty simple gauge and otherwise I'd have to find a hot cathode gauge and have probably some issues with that too.
So you'll have outgassing from that, right? Which now you'll have a lot of crosstalk between the two. So, I'm going to kind of, unless you have the cold cathode gauge right next to the ionizer of the RGA or right next to the detection region of the RGA, I doubt that you're having any problem. So it is a no-no if you don't know if it is a problem, but it's so easy to test, right? And in fact, what I will tell you is then, since you can remove the magnet, right, turn on the RGA, remove the magnet, and then bring the magnet to the RGA until you do see a problem. There won't be any residual effect from it, right? But bring it close to the ionizer, and you're going to see how close you can get before you have a problem. And bring it to the electromultiplier and see how close you can get. And that will give you a sense of where you need to be in the mounting position. This comes up all the time. Yeah. It's a common question.
I would like to thank Dr. Gerardo Brucker for the webinar. This is our first. Excuse our technical difficulties in the beginning, but we appreciate everyone for attending and hope that you would that you've gained additional knowledge and will help in your careers and on your jobs. Thank you so much, and we will follow up with further information at a later time.
Thank
Have
you,
a good evening,
Thank
everyone.
you.
Okay.
Thank you.
Bye-bye.
Thank you.